Look up at the night sky tonight, and you're not just seeing stars, you're witnessing the echoes of humanity's greatest quest. Every flicker of light represents centuries of curiosity, courage, and relentless discovery. This is the story of how we've pieced together the cosmos, one revelation at a time, and how each breakthrough has rewritten what we thought was possible. Welcome to the extraordinary journey of the 38 guiding lights of the universe, the milestones in astronomical discovery that have shaped our understanding of everything from the atoms in our bodies to the farthest edges of space. Think about the last time you felt truly small under that vast, starry canvas. That humbling moment is exactly where our story begins. Thousands of years ago, ancient astronomers carved their observations into stone, believing the heavens held the secrets of gods and destiny. Fast forward to today, where telescopes like Hubble and Webb peer billions of years into the past, capturing light from galaxies born near the dawn of time. What connects these moments? A single, unshakable human trait, the need to know what's out there. This video isn't just a list of discoveries, it's an epic tale of perseverance, where each chapter builds on the last, revealing how we've turned wonder into knowledge. From the first time someone realized the Earth wasn't the center of the universe, to the mind-bending confirmation of black holes, these 38 milestones are more than scientific achievements, they're waypoints in our collective journey to understand our place in the cosmos. Along the way, you'll meet the visionaries who dared to question the impossible, the tools that expanded our vision beyond imagination, and the moments that left even the brightest minds breathless. So settle in, because by the end of this journey, you won't just see the night sky differently, you'll feel it. The universe has been waiting to share its secrets, and together we're about to listen. Long before telescopes or satellites, the first astronomers looked up and saw not just lights in the sky, but a cosmic clockwork waiting to be decoded. Picture this: Babylonian scribes etching precise records of Venus's movements onto clay tablets over 3,000 years ago, or Egyptian priests aligning pyramids with the stars to mark the flooding of the Nile. These weren't just rituals, they were humanity's first scientific experiments. What's astonishing isn't just their dedication, it's how shockingly accurate they were without a single piece of modern technology. Take the Babylonians' prediction of lunar eclipses down to the hour, or the way Polynesian navigators used star paths to cross thousands of miles of open ocean. These cultures didn't just observe the heavens, they lived by them, turning celestial patterns into calendars, myths, and survival guides. But here's what truly connects us to these ancient stargazers. They asked the same questions we still wrestle with today. Why do the planets wander? What forces move the sun and moon? Their answers might have been wrapped in legend, gods riding chariots across the sky, or cosmic battles between light and darkness. Yet beneath those stories lay meticulous observations that would later fuel civilizations. The Greek astronomer Hipparchus, building on Babylonian data, mapped over 800 stars with naked eye precision. Meanwhile, half a world away, Mayan astronomers calculated the length of a year to within minutes, their temples doubling as astronomical observatories. What's easy to overlook is how radical these early discoveries were. Imagine insisting, as some Babylonian astronomers did, that celestial events weren't divine whims but predictable phenomena. That shift from myth to measurement was our species' first step toward real science, and while their tools were simple shadow sticks, aligned stones, knotted strings, their legacy is anything but. Every time a modern astronomer tracks an exoplanet's transit or models a galaxy's spin, they're standing on the shoulders of those first sky watchers who dared to believe the universe could be understood. Imagine living in a world where every sunrise and sunset wasn't just a daily miracle but proof that you stood motionless at the center of creation. That's exactly how Claudius Ptolemy saw the universe in the 2nd century, and his vision would shape human thought for the next 1400 years. His masterpiece, The Almagest, wasn't just a book. It was a cosmic rulebook that placed Earth firmly at the heart of everything, with planets, stars, and even the sun revolving around us in perfect, intricate circles. At first glance, it seems like the ultimate human ego trip, but here's the twist: Ptolemy's model worked. With painstaking precision, he mapped the planets' looping paths across the sky using a system of epicycles, tiny circles upon circles, that could predict celestial movements down to the hour. What's wild isn't that Ptolemy got it wrong, it's how brilliantly his wrongness functioned. Picture a clockmaker building an ornate timepiece with dozens of unnecessary gears, yet the hands still tell the right time. That's the Almagest. Sailors navigated oceans by it, farmers planned harvests around it, and scholars treated it as gospel. But beneath its polished calculations lay a deeper truth: science thrives on imperfections. Every time Ptolemy's models strained to explain Mars's backward dance or Venus's shifting brightness, it left cracks for future astronomers to pry open. And that's where the real magic happens. When Copernicus and Galileo finally challenged the geocentric view centuries later, they weren't just overturning an idea, they were standing on Ptolemy's shoulders. His obsessive data collection, his insistence on mathematical rigor, even his creative fudging with epicycles, all of it set the stage for the next revolution. Science doesn't leap from ignorance to truth in a single bound. It stumbles forward, borrowing tools from yesterday's mistakes to build tomorrow's breakthroughs. Ptolemy's universe may have been a cosmic illusion, but without it, we might never have learned to question what seems obvious. So the next time you hear someone call an old theory debunked, remember, even wrong answers can point us toward the right questions. Nicolaus Copernicus didn't just move the sun, he moved the entire universe. In the quiet corners of a 16th century Polish cathedral, this unassuming cleric scribbled equations that would shatter humanity's cosmic self-image. His radical idea, that Earth wasn't the stationary throne of creation but a mere passenger orbiting an ordinary star. Imagine the audacity of that moment, declaring, against 1400 years of Ptolemaic dogma, that the universe didn't revolve around us. His manuscript, De Revolutionibus Orbium Celestium, wasn't just a scientific paper, it was a silent bomb timed to detonate the medieval worldview. What's often overlooked is how terrifying this revelation truly was. This wasn't just about planetary motion, it struck at the heart of philosophy, religion, and human identity. If Earth wasn't central, were we still special? Did the heavens still care about us? Copernicus himself hesitated for decades, only publishing on his deathbed, perhaps fearing the backlash, and yet his math was undeniable. Those elegant circular orbits, though imperfect, explained celestial motions far more cleanly than Ptolemy's clunky epicycles. Suddenly, Mercury's erratic dance and Venus's phases made sense, not as celestial quirks, but as natural consequences of our new, humbler address in the cosmos. But here's the real genius of Copernicus. He didn't just change our location in space, he changed how we pursue truth. By trusting observation over authority, he handed humanity a new tool, the courage to question what everyone knows. When Galileo later turned his telescope to Jupiter's moons, when Kepler plotted Mars's elliptical path, they were standing on the foundation Copernicus laid. His revolution wasn't fought with swords, but with star charts and trigonometry, proving that sometimes the most powerful weapon is a better idea. And though he'd never lived to see it, his sun-centered universe would ignite a chain reaction of discovery. from Newton's gravity to Hubble's expanding cosmos, each breakthrough rooted in that first, fearless reimagining of the sky. Galileo Galilei didn't just peer through a telescope, he tore open the fabric of the cosmos. In the winter of 1610, when he first trained his handmade spyglass on Jupiter, he saw something impossible: 4 tiny stars clinging to the planet like loyal attendants. Night after night, he watched them shift positions, orbiting Jupiter itself. This wasn't just a discovery, it was heresy. According to the church and academic tradition, everything in heaven revolved around Earth, yet here was proof of moons circling another world. The implications were earth-shaking. If Jupiter could host its own celestial entourage, why couldn't Earth simply be another planet orbiting the Sun? But Galileo wasn't finished. Turning his telescope to Venus, he noticed something even more damning to the old worldview. The planet showed phases like the Moon, waxing and waning in a way only possible if it circled the Sun. These weren't theoretical arguments, they were visual, undeniable facts. Imagine the thrill and terror of that moment, realizing you're holding evidence that could upend centuries of belief. Galileo's sketches of Venus's crescent phase weren't just scientific notes, they were brushstrokes in a new cosmic portrait, one where Earth was no longer the stage, but a participant in a grander dance. What's often forgotten is the sheer guts it took to defend these discoveries. When the Inquisition demanded he renounce his findings, Galileo's eventual recantation, whispered under threat of torture, masked a quieter rebellion. Even house arrest couldn't stop him from smuggling out manuscripts that would keep the Copernican flame alive. His defiance wasn't just about astronomy, it set a precedent for science itself. Truth, he insisted, wasn't dictated by authority but written in the language of observation and math. Centuries later, when astronauts left Earth's gravity, they proved him right in the most poetic way possible, by looking back at our tiny, spinning world, just one among countless others in a universe far stranger and more beautiful than anyone had dared to dream. Johannes Kepler gazed at the stars not just as a mathematician, but as a cosmic detective, and what he uncovered would rewrite the rules of the solar system. While Copernicus had moved the Sun to the center and Galileo had glimpsed its satellites, it was Kepler who cracked the code of planetary motion itself. His 3 laws didn't just tweak the old models, they revealed a universe governed by elegant, predictable rhythms. Picture this: for centuries, astronomers had struggled to explain why Mars sometimes backtracked in the sky, looping in baffling retrograde motions. Kepler's breakthrough came when he abandoned a sacred assumption that planets moved in perfect circles. Instead, he proposed something radical. Orbits were elliptical, with the Sun slightly off-center, like a dancer pulling its planetary partners in closer at some points and letting them swing wide at others. That first law alone would have been revolutionary, but Kepler didn't stop there. His second law uncovered another secret: planets don't move at uniform speeds. They accelerate as they near the Sun, sweeping out equal areas in equal times. Think of it like a celestial ice skater spinning faster as they pull their arms in. Then came the piece de resistance, his third law, which tied a planet's orbital period to its distance from the Sun with mathematical precision. Suddenly, the solar system wasn't just orderly, it was quantifiable. A world that had once seemed chaotic now hummed with harmonic ratios, as if the planets were notes in a grand cosmic symphony. What's astonishing isn't just the accuracy of Kepler's laws, but how he derived them. Working with Tycho Brahe's meticulous observations of Mars data, so precise it included margins of error smaller than the width of a star in the night sky, Kepler spent years wrestling with calculations, discarding theory after theory until the numbers sang. His triumph wasn't just scientific, it was philosophical. The universe, he showed, wasn't a realm of divine whimsy but a machine of sublime geometry, one that humans could decode. And when Isaac Newton later stood on Kepler's shoulders to unveil gravity's universal pull, he'd simply be extending the truth Kepler first glimpsed. The heavens speak in mathematics, and those bold enough to listen might just hear their song. Isaac Newton didn't just see an apple fall, he saw the entire universe snap into focus. That famous moment in 1666, whether legend or fact, captures the spark of a revelation that would change everything. The same force pulling fruit from a tree also holds the moon in orbit around Earth. Until then, celestial and earthly physics had been separate realms, planets moved by divine perfection, while objects on Earth obeyed messy, mundane rules. Newton's genius was realizing these were two faces of the same force. His Philosophiae Naturalis Principia Mathematica, published in 1687, didn't just solve a puzzle, it rewrote the rules of reality. Imagine the sheer boldness of his claim. Every particle of matter, from a grain of sand to a distant star, pulls every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them. This wasn't just a theory, it was a cosmic glue binding the universe into a single, predictable system. Suddenly, Kepler's elliptical orbits weren't just observational quirks. They were mathematical necessities, the inevitable result of gravity's invisible tug. Newton's equations could predict the return of comets, the tides of the ocean, even the slight bulge of Earth's equator, all with breathtaking precision. But here's what truly set Newton apart. He didn't stop at explanation, he built tools. His calculus, invented alongside the laws of motion and gravity, gave scientists a language to describe change itself. Where earlier thinkers saw mysteries, Newton saw mechanisms. When Edmund Halley used his friend's laws to predict the return of a comet in 1758, later named Halley's Comet, it wasn't just a scientific victory. It was proof that the cosmos ran on knowable principles. Yet for all its power, Newton's gravity held a quiet humility. He famously wrote, "If I have seen further, it is by standing on the shoulders of giants," acknowledging Copernicus, Kepler, and Galileo. But his work also hinted at deeper mysteries like what gravity was, not just how it behaved. That question would simmer for centuries until Einstein reimagined gravity as the curvature of spacetime. Newton's universe was a clockwork, but his legacy was a key, one that unlocked not just answers but the next generation of questions. William Herschel wasn't looking for a planet that night in March 1781. He was simply mapping stars. The German-born musician turned amateur astronomer had built his own telescope, grinding mirrors with relentless precision to peer deeper into the sky than most professionals of his era. While scanning the constellation Gemini, he noticed a faint disk that refused to twinkle like a star. Assuming it was a comet, he noted its position and returned night after night, watching in growing astonishment as it moved against the fixed backdrop of stars. This was no comet. Its slow, stately orbit revealed it as something far more extraordinary, a new planet, the first discovered since ancient times. Herschel's identification of Uranus didn't just add another world to the solar system, it shattered an unspoken assumption. For millennia, humanity had believed the planetary lineup ended at Saturn, the ringed giant marking the outer frontier. Suddenly, the cosmic map had to be redrawn. The discovery sent shockwaves through scientific circles, not just for its novelty, but for what it implied. If one unknown planet had lurked unseen, who was to say others didn't? Herschel's find became a rallying cry for astronomers, proving the solar system was still full of surprises. What makes this milestone so pivotal isn't just the discovery itself, but how it happened. Herschel wasn't part of the academic elite. He was a self-taught outsider, proof that groundbreaking science could come from anywhere. His homemade telescope, with its 20-foot focal length, outperformed many professional instruments of the day, a testament to his ingenuity. King George III, impressed by the find, appointed him court astronomer, catapulting Herschel from amateur to celebrity overnight. Yet the real legacy of Uranus lies in the questions it provoked. Why was it tilted nearly 90 degrees on its axis? What caused its unusual magnetic field? These mysteries would take centuries to unravel, but they all stemmed from that single, humble observation. The ripple effects were immediate. Astronomers began scrutinizing the gaps between Mars and Jupiter, eventually uncovering the asteroid belt. Decades later, mathematical predictions based on Uranus's irregular orbit would lead to the discovery of Neptune. Herschel didn't just expand the solar system, he ignited a hunt for hidden worlds that continues to this day, from Pluto's icy plains to the hypothetical planet 9. His story reminds us that sometimes the most profound discoveries happen when we're looking for something else entirely, and that the universe always has another secret waiting just beyond the edge of our sight. Pierre-Simon Laplace looked at the clockwork precision of the solar system and asked a question no one had dared to voice so boldly. What if this perfect arrangement wasn't designed but born? In 1796, the French mathematician presented his nebular hypothesis, proposing that our sun and planets had condensed from a swirling cloud of gas and dust. This wasn't just another theory, it was a cosmic origin story stripped of divine hands, suggesting that even the grandest celestial structures emerged from simple physical laws. Imagine the audacity of that claim in an era when most still saw the heavens as immutable, God-crafted perfection. Laplace's vision began with a rotating nebula, collapsing under its own gravity like a slow-motion whirlpool. As it contracted, it spun faster, just as an ice skater pulls their arms in to accelerate, flattening into a disk where material clumped together over eons. The dense center became our sun, while smaller eddies in the disk formed planets. What's striking isn't just the elegance of this idea, but how much it got right centuries before we could test it. Modern telescopes have since captured newborn stars surrounded by protoplanetary disks, their swirling dust lanes mirroring Laplace's predictions with uncanny accuracy. Yet the real revolution lay in the philosophy behind the math. By framing planetary birth as a natural process, Laplace extended Newton's clockwork universe backward in time. No longer were planets fixed in place by celestial decree. They were dynamic survivors of a primordial dance, their orbits fossilized echoes of that ancient collapse. This shift resonated far beyond astronomy, quietly challenging the notion that nature required supernatural explanations. Even Laplace's famous, if apocryphal, reply to Napoleon, that his equations had no need for the hypothesis of God, captured the seismic implications. Science could now trace cosmic history without invoking miracles. Of course, later discoveries would refine his model. We now know magnetic fields and turbulence play crucial roles, and that planet formation is messier than Laplace imagined. But his core insight that gravity alone could sculpt worlds from chaos remains foundational. Every time astronomers spot a distant exoplanet or model stellar nurseries, they're building on that first daring premise. The universe makes itself one swirling cloud at a time. Giuseppe Piazzi wasn't hunting for asteroids on New Year's Day, 1801. He was compiling a star catalogue when he spotted an unassuming star in Taurus that didn't belong. Night after night, this faint dot crept against the fixed backdrop, too slow for a comet yet too small for a planet. Naming it Ceres after the Roman goddess of agriculture, Piazzi had unknowingly cracked open a cosmic vault, revealing an entirely new class of celestial objects. The scientific community buzzed with excitement, convinced they'd found the missing planet long predicted to orbit between Mars and Jupiter. But within a few years, as astronomers like Heinrich Olbers discovered similar bodies, Pallas, Juno, Vesta, the truth became clear. Ceres wasn't a lone world but the brightest member of a vast asteroid belt. This discovery shattered more than just expectations, it rewrote the solar system's architecture. Before Ceres, the orderly lineup of planets suggested a clean, empty space between Mars and Jupiter. Now suddenly that gap teemed with rocky fragments, remnants of a planet that never formed. The implications were staggering. If our solar system contained such debris, what did that say about how planets were born? Ceres and its siblings became celestial fossils, offering clues to the violent collisions and gravitational tug-of-wars that shaped our cosmic neighborhood. What's often overlooked is how Ceres itself defied categorization. For half a century, it was demoted from planet to asteroid, only to be reclassified in 2006 as a dwarf planet, a testament to its unique nature. Larger than some moons, yet small enough to share its orbit with countless other asteroids, Ceres blurred the lines between worlds and fragments. When NASA's Dawn spacecraft arrived in 2015, it unveiled a surprisingly active body with icy volcanoes and briny subsurface reservoirs, proving even minor solar system members could harbor major secrets. The real legacy of Piazzi's discovery lies in its humility. Ceres taught us that the universe doesn't conform to our tidy classifications. It's a messy workshop where failed planets become time capsules, and where what we dismiss as debris often holds the keys to grander truths. Every asteroid studied since, from near-Earth visitors to Trojan hitchhikers, traces its scientific lineage back to that first faint dot in Piazzi's telescope, a reminder that sometimes the smallest discoveries cast the longest shadows. Christian Doppler wasn't studying stars when he made his breakthrough, he was listening to sound waves. In 1842, the Austrian physicist noticed something peculiar about passing stagecoaches. Their horns seemed to pitch higher as they approached and lower as they sped away. This simple observation, now called the Doppler effect, would eventually transform astronomy. Doppler realized that just as sound waves compress or stretch with motion, light waves from moving objects should shift toward blue if approaching, toward red if receding. At the time, no instrument could measure such subtle color changes in starlight, but by 1868, British astronomer William Huggins pointed his spectroscope at Sirius and saw the proof. The star's telltale spectral lines had shifted slightly toward the red, revealing it was moving away from Earth at breathtaking speed. This revelation turned starlight into a cosmic speedometer. Suddenly, astronomers could calculate not just where stars were, but how they raced through space. Take binary star systems. By measuring the rhythmic red and blue shifts as stars orbited each other, scientists could deduce their masses and distances without ever leaving Earth. The Milky Way's rotation, mapped by tracking how its spiral arms twisted toward or away from us. But the real shock came in the 1920s when Edwin Hubble trained the 100-inch Hooker telescope on distant galaxies. Nearly everyone showed a redshift, and the farther away they were, the faster they appeared to flee. This wasn't random motion. It was evidence the universe itself was stretching, carrying galaxies along like raisins in rising dough. What's often overlooked is how this humble principle born from stagecoach horns solved one of astronomy's oldest riddles. For centuries, thinkers had assumed the cosmos was static and eternal. Doppler's effect, amplified by Hubble's observations, revealed a dynamic, evolving universe with a clear starting point. The Big Bang. Modern applications stretch even further. When exoplanet hunters detect a star's subtle wobble via Doppler shifts, they're using the same physics to find alien worlds. satellite navigation systems account for relativistic Doppler effects to keep GPS accurate. Even the James Webb Space Telescope relies on redshift to study the earliest galaxies, their light stretched into infrared by 13 billion years of cosmic expansion. The beauty of Doppler's discovery lies in its universality. Whether measuring a car's speed with radar or tracing the universe's expansion, the same principle applies: motion leaves fingerprints in waves. It's a reminder that sometimes the keys to the cosmos are hiding in plain sight, waiting for someone to listen closely. Gustav Kirchhoff and Robert Bunsen didn't just invent a new instrument, they gave astronomy a universal translator. In the 1850s, their groundbreaking work with prisms and flames revealed something astonishing. Every element, when heated, emits a unique fingerprint of light. Sodium burns yellow, copper flares green, and strontium blazes crimson, each color corresponding to precise wavelengths that could be split into spectral lines. But the real breakthrough came when Kirchhoff pointed this technique not at lab chemicals but at sunlight. The dark lines slicing across the solar spectrum matched the bright lines emitted by known elements on Earth. In that moment, the stars stopped being distant points of light and became open books, their pages written in the language of atoms. This was more than a scientific achievement, it was a cosmic revelation. For the first time, humans could decipher what the universe was made of without ever leaving Earth. Suddenly, astronomers realized that the same iron in your blood, the same calcium in your bones, and the same oxygen you breathe were forged in stellar furnaces billions of years ago. Spectroscopy didn't just analyze light, it connected us to the cosmos on an elemental level. When Kirchhoff identified sodium in the Sun's atmosphere, he proved that the laws of chemistry governing our planet were the same everywhere, from the Moon to the farthest visible star. What's often overlooked is how this tool transformed astronomy from a study of positions and motions to a science of composition and physics. Take the discovery of helium, named after Helios, the Greek sun god, when astronomers spotted an unknown spectral line in solar observations decades before the gas was found on Earth. Or the way Cecilia Payne-Gaposchkin used spectral data in 1925 to prove stars were overwhelmingly hydrogen and helium, overturning the then popular belief they shared Earth's rocky composition. Even today, when telescopes like Webb analyze exoplanet atmospheres for water vapor or methane, they're using the same fundamental principles Kirchhoff and Bunsen established. The real beauty of spectroscopy lies in its versatility. By studying whether spectral lines shift red or blue, astronomers measure cosmic motions, Doppler's effect in action. The width of lines reveals a star's temperature and pressure, while their intensity hints at magnetic fields. Modern instruments can even detect subtle wobbles in starlight caused by orbiting planets, turning spectra into exoplanet hunting tools. From identifying interstellar dust clouds rich in organic molecules to detecting lithium in ancient stars, spectroscopy remains astronomy's Swiss Army knife, one 19th-century innovation that continues to slice through the universe's greatest mysteries. Kirchhoff and Bunsen's flames have long cooled, but their legacy burns brighter than ever. Every time an astronomer points a spectroscope skyward, they're not just collecting data, they're reading the autobiography of the universe, written atom by atom in the light of distant suns. And the most humbling lesson of all, those pages tell us we're not just observers of the cosmos, but part of its story, a single chemical thread woven into an epic billions of years in the making. Urbain Le Verrier stared at the numbers in frustration. Something was stealing Uranus's gravity. For decades, astronomers had noticed the gas giant's orbit didn't quite match Newton's predictions, as if an unseen hand were tugging it off course. Most dismissed it as observational error, but the French mathematician became obsessed. Locked in his Paris observatory in 1846, he performed calculations so precise they bordered on prophecy. There had to be another planet beyond Uranus, he reasoned, its gravitational whisper warping the ice giant's path. When he sent his coordinates to Berlin's Johann Galle, the astronomer needed just 1 hour at his telescope to spot Neptune exactly where Leverrier's math said it would be, less than 1 degree off. This wasn't just a discovery, it was science's ultimate mic drop. For the first time, a planet had been found not by accident but by pure thought. Newton's laws had become a divining rod, revealing worlds through equations before light confirmed them. The implications were staggering. If gravity's rules could uncover Neptune, what else might they predict? Leverrier's triumph marked a turning point where astronomy stopped being merely observational and became predictive, a science that could see with mathematics as clearly as with telescopes. What's often forgotten is how close this breakthrough came to never happening. Across the English Channel, young mathematician John Couch Adams had independently calculated similar coordinates a year earlier. But Britain's Astronomer Royal, skeptical of such theoretical pursuits, delayed searching, a hesitation that cost them the glory. The rivalry that followed wasn't just about credit. It exposed a cultural divide between empiricists who trusted only observation and theorists who dared to let math lead the way. Neptune settled the debate. Both approaches were vital, two sides of the same celestial coin. The real magic lies in how Leverrier did it. Working backward from Uranus's orbital irregularities, he essentially played cosmic billiards, calculating where an unseen eighth planet must be to cause those deviations. His numbers weren't just right, they revealed Neptune's mass and orbit with astonishing accuracy. When Voyager 2 flew by in 1989, it found a world almost exactly as predicted. A blue marble of methane and hydrogen, whipped by supersonic winds with a storm system rivaling Jupiter's Great Red Spot. Yet Neptune's discovery left deeper ripples. It proved the solar system was still unexplored territory, sparking searches that would eventually find Pluto and the Kuiper Belt. More profoundly, it showed that science at its best doesn't just describe nature, it anticipates it. Every time modern astronomers predict an exoplanet's transit or model galaxy collisions, they're walking the path Leverrier carved. His pencil proved mightier than any telescope, revealing that sometimes the most powerful lens is the human mind. The year was 1920, and the stage was set for one of astronomy's greatest intellectual showdowns. On one side stood Harlow Shapley, a brash young scientist convinced our Milky Way was the entire universe, a vast island of stars with spiral nebulae like Andromeda, merely glowing gas clouds within it. Opposite him was Heber Curtis, a meticulous observer who dared to suggest those nebulae were island universes themselves, galaxies so distant their stars blurred into faint smudges. Their clash, later dubbed the Great Debate, wasn't just academic theater. It was a battle for the cosmic map, one that would redefine humanity's place in the grand scheme of things. Shapley's confidence came from his own groundbreaking work. Using Cepheid variable stars as cosmic yardsticks, he'd recently measured the Milky Way's staggering size, 100,000 light-years across, 10 times larger than previous estimates. But this triumph became his blind spot. If our galaxy was already so immense, he reasoned, how could anything lie beyond it? His opponents pointed to Andromeda's spiral structure and nova that flared brighter than any Milky Way star, but Shapley dismissed these as local phenomena. The debate's irony, both men were half right. Shapley correctly expanded our galaxy's boundaries but failed to see past them, while Curtis glimpsed the truth about external galaxies yet underestimated the Milky Way's scale. The real turning point came 3 years later when Edwin Hubble trained the 100-inch Hooker telescope on Andromeda. There, nestled in its spiral arms, he found Cepheid variables of his own, their pulsation rates revealing a distance so vast it shattered Shapley's model. Andromeda wasn't a nebula, it was a galaxy over 2 million light-years away, a twin to our own Milky Way. Suddenly, the universe unfurled into something unimaginably larger, with countless galaxies adrift in an ocean of darkness. The Great Debate's legacy wasn't just about who won, it was how science progresses. Two brilliant minds, each armed with partial truths, collided to illuminate a deeper reality. What makes this moment so pivotal is how it reshaped our cosmic perspective. Overnight, the Milky Way shrank from being the universe to one among billions, a single brushstroke in a sprawling galactic tapestry. Modern telescopes now peer back over 13 billion years, capturing galaxies in their infancy, but none of that would have been possible without this first fateful clash. The debate's true victor wasn't Curtis or Shapley. It was human curiosity itself, forever pushing against the edges of the known. Edwin Hubble peered through the eyepiece of the 100-inch Hooker telescope on a chilly Mount Wilson night in 1929, staring at photographic plates that held a secret about to rewrite cosmic history. Those smudges of light, distant galaxies like Andromeda weren't just far away, they were fleeing. By measuring their redshifts, Hubble noticed something astonishing. The farther a galaxy was, the faster it seemed to be receding from us. This wasn't random motion, it was a pattern so precise it could be plotted on a graph, revealing a universe stretching like an infinite loaf of raisin bread in the oven of time. What made Hubble's discovery revolutionary wasn't just the observation itself, but what it implied. If galaxies were racing apart now, then rewinding the cosmic film meant they must have once been crammed together in an unimaginably dense, hot state. The idea of a Big Bang wasn't Hubble's. That term came later, but his data provided the first concrete evidence that the universe had a birthday. Imagine the audacity of that realization. The stars, planets, and even the atoms in our bodies were traceable to a single explosive origin. Skeptics like Fred Hoyle famously resisted, preferring a steady-state universe, but Hubble's redshifts were relentless. The cosmos wasn't static, it was a dynamic, evolving entity with a clear starting point. The irony, Hubble almost missed his own breakthrough. His initial measurements suggested galaxies were moving at impossible speeds until he realized his distance calculations were off by a factor of 10. Even geniuses make mistakes, but what sets them apart is the rigor to correct them. Once he recalibrated, the pieces fell into place. The universe was expanding, and the rate of that expansion, now called the Hubble constant, became astronomy's most sought-after number. This revelation didn't just change cosmology, it redefined humanity's place in the grand scheme. No longer were we in a timeless, unchanging void, but a fleeting moment in a cosmic story still unfolding. Modern telescopes like Webb build on Hubble's legacy, peering back to galaxies so distant their light was emitted just after the Big Bang. Yet for all our progress, one question lingers. If the universe is expanding, what's fueling that expansion? Dark energy, the mysterious force driving galaxies apart faster and faster, is the next chapter in this saga, a reminder that every answer births new questions. Hubble's graph wasn't just data, it was a birth certificate for the cosmos, proving that even the universe has a history written in the light of fleeing galaxies. And just like that, the night sky ceased to be a static tapestry and became a living, breathing entity, one whose story we're only beginning to decode. Arno Penzias and Robert Wilson just wanted to eliminate static from their radio antenna instead. They stumbled upon the oldest echo in existence. In 1965, the two Bell Labs engineers were troubleshooting a persistent hiss in their Holmdel-Horn antenna, a leftover from early satellite communication tests. They scrubbed away pigeon droppings, realigned components, and even chased off nesting birds, but the noise refused to disappear. What they initially dismissed as an equipment flaw turned out to be something far grander: the cosmic microwave background radiation, a faint whisper of light from when the universe was a mere 380,000 years old. This accidental discovery wasn't just another scientific breakthrough, it was the smoking gun for the Big Bang theory. Decades earlier, physicists like George Gamow had predicted that if the universe began in a fiery explosion, its cooling remnants should permeate space as microwave radiation. Penzias and Wilson had unknowingly tuned into that signal, a relic so pristine it painted a picture of the cosmos before stars or galaxies even existed. The implications were staggering. Here was direct evidence that the universe hadn't always been here. It had a dramatic birth, and its afterglow still bathed everything in a frigid sea of microwaves, just 3 degrees above absolute zero. What's often overlooked is how perfectly this discovery dovetailed with earlier theories. When Princeton researchers Robert Dick and Jim Peebles heard about the Bell Labs team's findings, they immediately recognized it as the missing piece of their own cosmological models. The cosmic microwave background wasn't just noise, it was a snapshot of the infant universe, its tiny temperature variations revealing the seeds of all future structure. Those faint ripples would eventually collapse under gravity to form galaxies, stars, and planets, including our own. Modern telescopes like the Planck satellite have since mapped this radiation with exquisite detail, turning it into a time machine. By analyzing its subtle fluctuations, cosmologists can reconstruct the universe's composition down to the percentage of dark matter and dark energy. Yet for all its precision, the cosmic microwave background still holds mysteries. Why is one half of the sky slightly warmer than the other? Could strange patterns in the day to hint at other universes? Penzias and Wilson's frustration with that pesky static opened a window to questions we're still trying to answer today. Their story reminds us that sometimes the universe's greatest secrets hide in plain sight, not in grand revelations, but in the stubborn hum of an antenna that refused to stay quiet. And that faint hiss, it's still there, coursing through space as a reminder that every one of us is bathed in the afterglow of creation itself. Mitchell Mayer and Didier Queloz weren't looking to rewrite astronomy textbooks when they pointed their telescope at 51 Pegasi in 1995. They were simply testing a new instrument. The star, just 50 light-years away, seemed unremarkable, another sun-like dot in the constellation Pegasus. But what their spectrograph detected sent shockwaves through the scientific community. A rhythmic wobble in the star's light, shifting back and forth every 4.2 days. This wasn't stellar activity, it was the gravitational tug of an orbiting planet, one unlike anything in our solar system. Dubbed 51 Pegasi b, this world was a Jupiter-sized behemoth hugging its star closer than Mercury orbits our Sun, a hot Jupiter defying all expectations of where giant planets could exist. The discovery shattered centuries of assumptions. Since Copernicus, we'd assumed other stars hosted planets, but no one had proof until now. The real surprise wasn't just that exoplanets existed, but how strange they could be. Conventional wisdom said giant planets formed in cold outer orbits, yet here was one baking next to its star, challenging every model of planetary formation. Skeptics initially dismissed the signal as a starspot or pulsation, but Mayer and Queloz's meticulous data held up. Their breakthrough hinged on the radial velocity method, tracking how a star's light reddens and blue shifts as an orbiting planet's gravity pulls it subtly toward and away from us. This delicate dance, measurable as a change in starlight's wavelength by just meters per second, revealed a hidden cosmic choreography. Overnight, the floodgates burst open. Within a decade, astronomers found over 100 exoplanets, many equally bizarre. Super-Earths between rocky and gaseous worlds, puffy planets with the density of styrofoam, even rogue planets untethered to any star. The Kepler Space Telescope's launch in 2009 turned the trickle into a deluge, discovering thousands more by watching for the telltale dimming as planets crossed their stars' faces. Each new world expanded the playbook of what planetary systems could look like, some with planets packed tighter than peas in a pod, others with orbits more elliptical than comets. What makes 51 Piazzi B's discovery so pivotal isn't just the confirmation of exoplanets, it's how it transformed the search for life. Suddenly, the Drake equation's estimate of habitable worlds had real data to plug in. When astronomers later found planets in the Goldilocks zone of stars like TRAPPIST-1, where liquid water could exist, the question shifted from whether Earth-like planets exist to how many. Modern missions like JWST now analyze exoplanet atmospheres for biosignatures, oxygen, methane, even industrial pollutants, clues that might hint at alien biology. Yet the deepest lesson of Mayer and Queloz's find lies in its humility. After centuries of speculation, the first exoplanet we spotted wasn't a twin of Earth, but a cosmic oddball no one predicted. The universe, it seems, delights in confounding our expectations, and the more we explore, the clearer it becomes that we've only scratched the surface of planetary diversity. Every time a new world joins the catalog, we're reminded that the cosmos writes its own rules, and Earth is just one verse in an endless celestial poem. Fritz Zwicky stared at the Coma galaxy cluster through his telescope in the 1930s and saw something that shouldn't be possible. The galaxies were moving too fast. According to Newton's laws, the visible mass of stars and gas in the cluster couldn't possibly generate enough gravity to hold them together at those speeds. The system should have flown apart eons ago, yet there it was, defying physics. Zwicky, never one to mince words, called the missing mass Dunkel Materie, a dark matter. At the time, most astronomers dismissed it as a fringe idea, an error in measurement, or a quirk of Zwicky's famously combative personality. But decades later, Vera Rubin's meticulous observations of spinning galaxies confirmed the impossible. Stars at the edges of spiral galaxies orbited just as fast as those near the center, as if invisible halos of mass were anchoring them in place. What makes dark matter so baffling isn't just its invisibility, it's how much of the universe it controls. Ordinary matter, the stuff of planets, stars, and our bodies, accounts for a mere 5% of the cosmos. Dark matter outweighs it 5 to 1, weaving an unseen scaffold that guides the formation of galaxies and bends the fabric of spacetime itself. We know it exists because of its gravitational fingerprints, the way it distorts distant starlight like a cosmic funhouse mirror, or how it sculpts the vast cosmic web where galaxies cluster along invisible threads. Yet despite its dominance, dark matter refuses to reveal its true nature. It doesn't absorb, emit, or reflect light. It barely interacts with normal matter at all. The hunt for dark matter has become one of science's greatest detective stories. Underground labs shield detectors from cosmic rays, waiting for the rare collision between a dark matter particle and an atom. Particle accelerators like the Large Hadron Collider smash protons together at near light speeds, hoping to create dark matter in the debris. Even space telescopes map its distribution by tracing how its gravity warps the light of ancient galaxies. Leading theories suggest it could be WIMP, weakly interacting massive particles, actions, or even primordial black holes. But after decades, no experiment has captured it directly. The irony is poetic. We've charted galaxies billions of light years away, decoded the birth cries of the universe, and landed probes on distant worlds, yet the majority of reality remains hidden in plain sight. Dark matter's mystery reminds us that the cosmos still holds cards close to its chest. Every time astronomers map its gravitational shadow or simulate its role in the universe's infancy, they're piecing together a puzzle where the most important pieces are, quite literally, missing. And perhaps that's the most humbling lesson of all. The universe isn't just what we see, it's what we can't. The Hubble Space Telescope didn't just take pictures, it rewrote the cosmic atlas. When the shuttle Discovery carried it into orbit in 1990, astronomers expected sharper views, but no one anticipated how profoundly it would alter our understanding of the universe. Freed from Earth's turbulent atmosphere, Hubble's razor-sharp gaze captured light that had traveled billions of years, turning faint smudges into sprawling galaxies, each a whirlpool of stars and dust. Suddenly, the distant cosmos wasn't just observable, it was vivid, dynamic, and breathtakingly detailed. One of Hubble's earliest triumphs was solving a mystery that had gnawed at astronomers for decades: the age of the universe. By precisely measuring the pulsations of Cepheid variable stars in distant galaxies, Hubble's data refined the expansion rate of the cosmos, revealing the universe was roughly 13.8 billion years old. But its greatest legacy lies in the images that seared themselves into public consciousness, the pillars of creation in the Eagle Nebula, where towering columns of gas cradled newborn stars. The Hubble Deep Field, a seemingly empty patch of sky transformed into a mosaic of thousands of galaxies, each a flickering candle in the vast dark. These weren't just scientific data, they were windows into the universe's soul. What made Hubble revolutionary wasn't just its optics, but its adaptability. Designed to be serviced by astronauts, it evolved over 5 servicing missions, receiving upgraded cameras and instruments that kept it on the cutting edge for decades. Its observations confirmed the existence of supermassive black holes lurking in galactic cores, traced the aftermath of comet Shoemaker-Levy 9's collision with Jupiter, and even helped discover dark energy by observing distant supernovae. Hubble became more than a telescope, it was humanity's shared eye on the cosmos, its images gracing textbooks, screensavers, and museum walls. Yet Hubble's journey wasn't without drama. A flaw in its primary mirror, discovered weeks after launch, threatened to render it a billion-dollar failure. But in a stunning feat of ingenuity, engineers designed corrective optics, essentially cosmic glasses, that restored its vision. That near disaster became a testament to human persistence, proving that even our stumbles can lead to triumphs. Now, as Hubble shares the sky with successors like the James Webb Space Telescope, its legacy endures. It taught us that the universe is stranger and more beautiful than we'd imagined, that galaxies evolve violently, merging and cannibalizing one another, and that even the void of space teems with unseen wonders. Most of all, Hubble reminded us that exploration isn't just about answering questions, it's about learning which questions to ask next. Every time we gaze at one of its iconic images, we're not just seeing the universe, we're seeing our place within it, framed by a lens that turned the heavens into a mirror. For over a century, Einstein's general theory of relativity predicted them ripples in the fabric of spacetime itself, stretching and squeezing the cosmos like waves across an invisible ocean. Yet even Einstein doubted we'd ever detect gravitational waves. They were too faint, he thought, drowned out by the noise of the universe. Then, on September 14, 2015, at precisely 5:51 in the morning Eastern Time, twin detectors in Louisiana and Washington State caught something extraordinary. A chirp less than a second long rippling through LIGO laser beams. That fleeting signal, caused by two black holes colliding 1.3 billion light-years away, wasn't just proof of gravitational waves. It was humanity's first direct encounter with the warped geometry of spacetime, a phenomenon so elusive it took 40 years and $1 billion worth of engineering to catch it. What LIGO detected that day was the death spiral of two monstrous black holes, each about 30 times the mass of our Sun. Locked in a final, frantic dance, they whirled around each other hundreds of times per second before merging into a single, more massive black hole. In that cataclysm, an amount of energy equivalent to 3 suns converted into gravitational waves, radiating outward at light speed. By the time those waves reached Earth, they'd stretched and compressed space itself by 1,000th the width of a proton, a distortion so tiny it's like measuring the distance to Alpha Centauri to within the width of a human hair. The real magic lies in how LIGO spotted these whispers from the abyss. Each detector is an L-shaped vacuum chamber with arms 4 kilometers long. A laser beam splits down both arms, bouncing off mirrors to recombine at the center. Normally, the beams cancel each other out, but when a gravitational wave passes through, it minutely alters the arm's lengths, making the lasers briefly fall out of sync. That microscopic mismatch, smaller than the nucleus of an atom, is what LIGO supercomputers translated into the now famous chirp. This discovery didn't just confirm Einstein, it handed astronomers an entirely new sense. Before LIGO, we studied the universe through light, from radio waves to gamma rays. Now we can hear it. Gravitational waves carry information no telescope can capture. The secret lives of black holes, the shudders of neutron stars, even echoes from the Big Bang itself. Already, LIGO and its European counterpart Virgo have detected mergers involving neutron stars, events so violent they forge gold and platinum in their wake. Perhaps most thrilling is what this means for the future. Next-generation detectors like the space-based LISA mission could sense waves from supermassive black holes merging at the dawn of time. We're no longer just stargazers, we're spacetime listeners, tuning into the universe's hidden symphony. And that first chirp, it wasn't the end of a quest, but the opening note in a cosmic revolution. For centuries, black holes existed only as mathematical ghosts predicted by Einstein's equations but never seen. Then, on April 10, 2019, humanity peeled back the veil. The Event Horizon Telescope collaboration unveiled something unprecedented. A fiery ring of light encircling an abyss of darkness at the heart of galaxy M87. This wasn't an artist's impression or a simulation. It was the first direct visual evidence of a black hole's shadow, a sight so elusive even Einstein doubted we'd ever witness it. What made this image revolutionary wasn't just the confirmation that black holes exist. It was how the picture matched theoretical predictions with uncanny precision. The bright ring, superheated gas swirling at nearly light speed before vanishing past the event horizon. The point of no return, the dark center, the black hole's shadow, where gravity warps spacetime so severely that not even light can escape. This cosmic bullseye, 55 million light-years away, looked almost exactly as physicists had imagined for decades. Capturing this image required an audacious feat of engineering. The Event Horizon Telescope wasn't a single instrument, it was a virtual observatory spanning the globe, linking radio dishes from Hawaii to the South Pole. By synchronizing these telescopes with atomic clocks, astronomers created an Earth-sized interferometer, achieving resolution sharp enough to spot a donut on the moon. But even then, challenges mounted. Weather had to cooperate simultaneously across continents. Petabytes of raw data, recorded on stacks of hard drives, were flown to central processing centers since the internet couldn't handle the transfer. Then came the painstaking task of stitching together the fragments like assembling a jigsaw puzzle where half the pieces were missing. The result wasn't just a scientific triumph, it was a testament to human collaboration. Over 200 researchers across 60 institutions worked for years, battling technical hurdles and skepticism. Their success opens a new era of black hole astronomy. Already, the same team has captured our Milky Way's supermassive black hole, Sagittarius, a star, revealing its surprisingly quiet nature compared to M87's voracious counterpart. Future upgrades aim to add space-based telescopes, sharpening our view further. Most profoundly, this blurry orange ring reminds us that the universe's most mysterious objects aren't beyond our reach. With ingenuity and persistence, we can photograph the unseeable, turning mathematical abstractions into tangible reality. And as we peer deeper, who knows what other cosmic phantoms might step into the light? The James Webb Space Telescope isn't just another observatory, it's a time machine. When it launched on Christmas Day 2021, perched atop an Ariane 5 rocket, it carried humanity's hopes to see further back than ever before. Unlike Hubble, which primarily captures visible light, JWST is tuned to infrared wavelengths, the silent whispers of heat left over from the universe's infancy. This shift in perspective is like swapping a flashlight for night vision goggles, revealing celestial objects too cold or distant to glow in visible light. Picture this: some of JWST's first targets were galaxies over 13.4 billion light-years away. Their light emitted when the universe was barely 2% of its current age. These aren't just ancient star clusters, they're cosmic toddlers, caught in the act of forming when the cosmos was a chaotic nursery of raw elements. What's staggering isn't just their distance, but how different they appear. Unlike modern galaxies, these early structures are smaller, clumpier, and brimming with young, hot stars that blaze with ultraviolet fury. JWST infrared eyes pierce through the dust that shrouds these primordial giants, capturing details Hubble could only dream of. But the telescope's ambitions stretch far beyond galactic archaeology. Hovering at Lagrange Point 2, a gravitational sweet spot a million miles from Earth, JWST turns its golden hexagonal mirrors toward exoplanets with the precision of a cosmic detective. When a distant world passes in front of its star, the telescope dissects the starlight filtering through its atmosphere, hunting for molecular fingerprints, water vapor, carbon dioxide, even methane. In 2023, it made headlines by detecting potential biosignatures on the Hycean planet K218b, a water-rich world with hints of dimethyl sulfide, a gas produced by marine life on Earth. While far from proof of aliens, findings like these mark the first steps toward answering one of humanity's oldest questions: are we alone? What truly sets JWST apart is its ability to witness cosmic birth in real time. In the Orion Nebula, it's captured newborn stars shredding their dusty cocoons with violent stellar winds, while in the Carina Nebula, its images reveal towering pillars of gas where protoplanetary disks, future solar systems, are taking shape. These snapshots aren't just beautiful, they're rewriting textbooks on star formation, showing the process is messier and more dynamic than models predicted. Yet for all its power, JWST's journey to the launchpad was fraught with tension. Plagued by delays and budget overruns, the project nearly collapsed multiple times. Its 18 beryllium gold mirror segments had to unfold flawlessly in deep space, a maneuver so complex engineers called it 30 single points of failure. The telescope's sun shield, spanning a tennis court's length, had to deploy perfectly to block heat from the sun, moon, and Earth, chilling JWST instruments to -387 degrees Fahrenheit. Now, as it beams back data, JWST is doing more than fulfilling promises, it's surprising us. From galaxies too massive to exist so early in cosmic history to the unexpected chemistry of exoplanet skies, every discovery challenges assumptions. This telescope isn't just showing us the universe as it is, it's revealing how much we still have to learn. And with decades of operation ahead, its greatest revelations may still be waiting in the dark, ready to rewrite our story once more. The Voyager missions weren't just spacecraft, they were time capsules hurled into the cosmos with the audacity of a civilization ready to introduce itself to the universe. Launched in 1977 within weeks of each other, Voyager 1 and 2 capitalized on a rare planetary alignment that occurs only once every 176 years. This celestial shortcut allowed them to slingshot from Jupiter to Saturn and beyond on gravity assists, a maneuver so precise it was like threading a needle across billions of miles. Their targets, the mysterious outer planets, gas giants that had until then been little more than blurry smudges in even the most powerful telescopes. What Voyager found at Jupiter shattered every expectation. The spacecraft revealed the planet's Great Red Spot as a colossal storm system, larger than Earth and raging for centuries. But the real showstoppers were its moons. Io, a pizza-colored world pockmarked with active volcanoes spewing sulfur hundreds of miles high, proved that planetary geology didn't require internal heat from radioactive decay. Jupiter's gravitational kneading could power volcanic fury all on its own. Europa, cloaked in a cracked icy shell, hid a subsurface ocean that still ranks as one of the solar system's most promising places to hunt for life. These weren't dead rocks, they were dynamic worlds, each with its own dramatic story. Saturn brought even more revelations. Voyager 1's close pass exposed the intricate structure of its rings, thousands of shimmering bands sculpted by shepherd moons and resonant gravitational dances. But it was Voyager 2, reprogrammed mid-flight to continue onward to Uranus and Neptune, that truly pushed the envelope. At Uranus, it discovered a planet knocked on its side, its poles alternately baking in decades-long sunlight or frozen in darkness, with magnetic fields askew like a compass needle gone haywire. Neptune, when Voyager 2 finally arrived in 1989, stunned scientists with supersonic winds and the Great Dark Spot, a storm rivaling Jupiter's, in an atmosphere scientists had assumed would be too sluggish for such violence. Yet the Voyager's most profound legacy wasn't just what they found, but where they went next. Sailing past Neptune, Voyager 1 turned its camera backward in 1990 to snap the iconic, pale blue dot image, Earth reduced to a single pixel suspended in a sunbeam. Then, in 2012, it crossed the heliopause, the boundary where the sun's influence wanes and interstellar space begins. The data it sent back was surreal, a 50% increase in cosmic rays, a sudden drop in solar particles, and the faint hum of plasma vibrations, the first sounds ever recorded from between the stars. Voyager 2 followed 6 years later, confirming that our solar system isn't a perfect bubble but a porous, asymmetrical structure, dented and warped by the galactic winds. What's astonishing isn't just the distance these probes have traveled, over 14 billion miles and counting, but how they've done it. Running on processors weaker than a modern car key fob, powered by decaying plutonium batteries, and communicating with Earth via a 23-watt transmitter about as strong as a refrigerator light bulb. The Voyagers are triumphs of analog-era engineering. Their golden records, etched with greetings in 55 languages, whale songs, and even Chuck Berry's Johnny B. Good, remain humanity's calling card to any civilization that might one day intercept them. Now, as they drift farther into the void with instruments slowly shutting down, their final gift may be philosophical. the voyagers remind us that exploration isn't just about discovery, it's about perspective. They've shown us that even the most distant planets are part of our neighborhood, that our sun is just one light among countless others, and that the urge to reach beyond what we know is coded into our very DNA. Long after their last signal fades, their legacy will endure not just in textbooks, but in the way they reshaped how we see ourselves, adrift on a pale blue dot in the vast cosmic ocean. Clyde Tombaugh spent countless frigid nights hunched over a blinking comparator at Lowell Observatory in 1930, painstakingly examining photographic plates under a magnifying glass. The 24-year-old farm boy turned astronomer was searching for a mysterious Planet X, predicted to orbit beyond Neptune, but what he found would ignite both celebration and controversy for decades to come. On February 18th, after nearly a year of methodical searching, Tombaugh spotted a tiny dot shifting position against the starfield between plates taken 6 days apart. This faint, slow-moving speck, later named Pluto after the Roman god of the underworld, became the first and only planet discovered by an American and the solar system's most distant known member. The excitement was immediate. Newspapers hailed Pluto as the 9th planet, school textbooks were updated, and Walt Disney even named Mickey Mouse's pet dog in its honor. Yet from the beginning, Pluto stood apart. Its orbit was oddly tilted and elongated, crossing Neptune's path like a cosmic daredevil. Early estimates suggested it might be Earth-sized, but by the 1970s, astronomers realized it was smaller than our moon, just 1/500th Earth's mass. Then came the real shocker. Pluto wasn't alone. The discovery of its largest moon, Charon, in 1978 revealed a binary system where both worlds orbited a shared point in space, dancing like celestial partners locked in a gravitational embrace. The hammer fell in 1992 when astronomers found the first object in what we now call the Kuiper Belt, a vast ring of icy bodies beyond Neptune. Suddenly, Pluto wasn't an oddball planet, but the brightest member of a whole new class of solar system objects. As more Kuiper Belt objects turned up, some nearly Pluto's size, the International Astronomical Union faced a dilemma: either declare dozens of new planets or redefine what planet meant. In 2006, they chose the latter, establishing 3 criteria: orbiting the Sun, having enough gravity to be round, and clearing its orbital neighborhood. Pluto failed the third test, becoming the first dwarf planet, a decision that sparked public outcry and even a mocking resolution by the New Mexico legislature in Tombaugh's adopted home state. Yet Pluto's demotion only made it more fascinating. When NASA's New Horizons probe finally reached it in 2015 after a 9-year journey, it revealed a shockingly dynamic world. Towering mountains of water ice rose higher than the Rockies, vast glaciers of frozen nitrogen flowed like slow-motion honey, and a heart-shaped plain named Tombaugh Regio hinted at geological activity beneath the surface. Charon, meanwhile, boasted a canyon system dwarfing the Grand Canyon and mysterious red stains at its pole. These weren't dead relics but active worlds reshaped by processes we're still struggling to understand. What makes Pluto's story so compelling isn't just the science, it's how it reflects our evolving relationship with the cosmos. Tombaugh's discovery expanded our horizons, while its reclassification reminded us that scientific categories aren't set in stone. The Kuiper Belt, once hypothetical, now teems with thousands of known objects, some potentially harboring underground oceans. Pluto, far from being diminished, became a gateway to this unexplored frontier, proof that even in our own cosmic backyard, there are still wonders waiting to rewrite the rules. Its icy plains and hazy layers whisper a humbling truth: the universe doesn't care about our labels. It simply is in all its messy, glorious complexity. Jan Ewart stared at the paths of long-period comets in the 1950s and noticed something peculiar: they weren't arriving from random directions. Instead, these icy visitors, like Halley's Comet, seemed to originate from a vast spherical shell at the solar system's outermost edge. His calculations suggested a place so distant it defied imagination, a frozen reservoir of trillions of comet nuclei, stretching nearly a light year from the Sun, far beyond even Pluto's orbit. This hypothetical region, now called the Oort cloud, wasn't just a scientific curiosity. It was the missing link explaining where comets came from and why some hurtle inward on orbits lasting millions of years. What makes Ewart's proposal so revolutionary is how it explained cometary chaos with celestial geometry. Before his work, astronomers struggled to reconcile why some comets returned like clockwork while others appeared once and vanished forever. The Oort cloud provided the answer. Gravitational nudges from passing stars or galactic tides could dislodge these icy bodies, sending some spiraling toward the Sun as dazzling visitors while others drifted into interstellar space. Picture a cosmic game of pool where the slightest tap sends comets careening inward, their frozen surfaces vaporizing into the iconic tails we associate with them. Yet despite its theoretical elegance, the Oort cloud remains the solar system's last great unobserved frontier, too distant and faint for current telescopes to spot directly. The scale of this region is almost incomprehensible. If the Sun's influence ends at the heliopause where Voyager probes entered interstellar space, the Oort cloud extends 1,000 times farther. To put it in perspective, if Earth were a marble in New York City, the Oort cloud's inner edge would sit near Los Angeles with its outer reaches stretching to the Moon. This vast distance means the comets here are pristine time capsules, untouched by solar heat for billions of years, preserving the original ingredients of our solar system's birth. Modern simulations suggest the Oort cloud isn't just a relic of our solar system's formation, but a galactic crossroads. Computer models show it likely contains interstellar interlopers, comets captured from other stars during the Sun's infancy when stellar neighbors were closer. Some scientists even speculate that rogue planets or brown dwarfs might lurk in its icy depths, their gravity subtly bending the paths of known comets. Future missions like the proposed interstellar probes could one day venture into this realm, but for now, it remains a shadowy realm of inference and wonder. The beauty of Ewart's hypothesis lies in its predictive power. When astronomers detect comets like 2017's Oumuamua, the first known interstellar visitor, its trajectory hints at the existence of similar clouds around other stars. Each new comet studied, from the spectacular Hale-Bopp to the recently discovered Bernardinelli-Bernstein, adds another piece to the puzzle, revealing how these icy nomads bridge the gap between our solar system and the galaxy beyond. So while we may never directly image the Oort cloud in our lifetimes, its influence is written across the night sky every time a comet flares to life. It's a reminder that even in the farthest, darkest reaches of our cosmic neighborhood, the universe is anything but empty, just waiting for the right moment to send another frozen messenger streaking into view. Frank Drake pointed his radio telescope at two sun-like stars in 1960, not knowing if anyone or anything would be listening. The young astronomer's modest project, dubbed Project Ozma, marked the dawn of humanity's most profound quest, the search for extraterrestrial intelligence. For 3 months, Drake trained his antenna on Tau Ceti and Epsilon Eridani, scanning for patterns in the cosmic static that might betray the presence of another civilization. The silence that followed wasn't discouragement, it was the first note in a symphony of curiosity that's still playing today. What makes SETI so compelling isn't just the science, it's the audacity of the question itself. Are we alone? Drake formalized this uncertainty with his now famous equation in 1961, a deceptively simple string of variables estimating the number of communicative civilizations in our galaxy. Plug in the rate of star formation, the fraction with planets, the odds of life arising each term a Russian nesting doll of unknowns. The equation's brilliance lies not in its answers, but in how it frames the search as a series of testable hypotheses. Suddenly, the hunt for aliens wasn't science fiction. It was a scientific workflow, one that's driven decades of research across astronomy, biology, and engineering. Modern SETI has evolved far beyond Drake's humble beginnings. Arrays like the Allen Telescope survey scan thousands of stars simultaneously, passing millions of radio channels for the telltale narrow-band signal that nature struggles to produce. Optical SETI hunts for laser pulses flickering across interstellar distances, while Breakthrough Listen analyzes petabytes of data with machine learning, searching for anomalies even human experts might miss. The tools have grown sophisticated, but the core philosophy remains unchanged. If someone out there is transmitting, we should be listening. Yet SETI's true legacy isn't just in the silence, it's in the unexpected discoveries along the way. When astronomers identified fast radio bursts, mysterious millisecond flashes from distant galaxies, some dared to hope they might be artificial. While natural explanations now seem more likely, that tantalizing uncertainty propelled new studies of extreme astrophysics. The infamous WOW signal, a 72-second burst detected in 1977, still defies full explanation, a reminder that the cosmos loves to keep us guessing. Even failed searches yield dividends, like the way SETI signal processing techniques now help track endangered species or monitor brain activity. The skeptic's question lingers. After 60 years of searching, why haven't we found anything? Possible answers span the philosophical to the statistical. Maybe civilizations are rarer than we hoped, their transmissions drowned in the galaxy's radio cacophony. Perhaps they've moved beyond radio to technologies we can't yet detect, like neutrino communication or quantum entanglement. Or it could be that advanced societies self-destruct before achieving interstellar dialogue, a sobering counterpoint to our own planetary challenges. What keeps SETI alive isn't evidence but imagination. Every exoplanet discovered in the habitable zone, every extremophile bacterium found in Earth's harshest environments, expands the boundaries of where life might thrive. Initiatives like METI, Messaging Extraterrestrial Intelligence, flip the script, actively broadcasting greetings to nearby stars despite ethical debates about announcing our presence. Meanwhile, projects like SETI at home have democratized the search, letting anyone contribute spare computer power to sift through cosmic noise. The most profound shift may be cultural. Once fringe, the search for alien intelligence now informs NASA, astrobiology roadmaps, and garners funding from tech billionaires. The James Webb Space Telescope's ability to analyze exoplanet atmospheres for biosignatures owes a debt to SETI's foundational question: what does life in all its forms look like from light years away? As antennas continue scanning and lasers pierce the dark, SETI embodies a paradox unique to science. The longer we search without success, the more significant the search becomes. Whether we eventually hear a whisper across the stars or come to terms with cosmic solitude, the act of listening transforms us. It's a mirror held up to humanity's best instincts: curiosity, humility, and the stubborn belief that even in an unfathomably vast universe, connection might still be possible. 26 years ago, a microwave oven-sized robot named Sojourner rolled onto Martian soil, becoming the first wheeled explorer to touch another planet. That modest six-wheeled rover, part of NASA's Pathfinder mission in 1997, wasn't just a technological marvel, it was the vanguard of a revolution. For 90 days, Sojourner analyzed rocks with its alpha proton X-ray spectrometer, revealing a Mars far more complex than the barren wasteland we'd imagined. Its tiny tracks in the rust-colored dust marked the beginning of something extraordinary, the transformation of Mars from a distant red dot into a world of towering canyons, ancient riverbeds, and tantalizing hints of a watery past where life might have once thrived. Fast forward to 2021, and Perseverance, a car-sized laboratory on wheels drilled into Jezero crater, a site scientists believe was once a sprawling lake. The difference in capability is staggering. Where Sojourner could move at a snail's pace of 1 centimeter per second, Perseverance navigates autonomously, choosing its own path around boulders while its super-cam zaps rocks with lasers to analyze their chemistry. Its mission, to hunt for biosignatures, chemical traces left by ancient microbial life, and cache samples for a future return to Earth. But perhaps its most poetic payload is Ingenuity, the first aircraft to fly on another world, whose rotor blades sliced through Mars' thin air like a hummingbird in slow motion, proving powered flight was possible in an atmosphere just 1% as dense as Earth. Between these bookends, a lineage of robotic pioneers reshaped our understanding of the Red Planet. Spirit and Opportunity, launched in 2003, became the marathon runners of Mars exploration. Designed for 90-day missions, they lasted years, with Opportunity logging an astonishing 28 miles before succumbing to a global dust storm in 2018. Their discoveries were paradigm-shifting. Opportunity found hematite, blueberries, tiny spheres formed in ancient water, while Spirit uncovered silica-rich deposits hinting at past hydrothermal activity. These weren't just geological quirks, they were pieces of a puzzle suggesting Mars once had the ingredients and environment suitable for life. Then came Curiosity in 2012, a mobile laboratory the size of an SUV. Its drill bored into Martian bedrock, uncovering organic molecules, the carbon-based building blocks of life, in Gale crater. Even more startling was its measurement of methane fluctuations in the atmosphere, a gas often produced by biological activity on Earth. While non-biological processes can also create methane, the finding ignited debates that still rage today. Could Mars be hiding microbial life beneath its surface, even now? What makes these rovers so remarkable isn't just their scientific haul, it's how they've turned Mars into a tangible place. Through their cameras, we've watched sunsets paint the sky in ethereal blues, felt the crunch of wheels over gravelly regolith, and marveled at dust devils spiraling across plains. They've weathered radiation storms, navigated sand traps, and even sung "Happy Birthday" to themselves via sample analysis vibrations. Each rover has carried a piece of human ingenuity to Mars, from Opportunity's aluminum hull crafted from World Trade Center steel to Perseverance's plaque honoring healthcare workers during the pandemic. Now, as Perseverance collects samples for the ambitious Mars Sample Return Campaign, a multi-mission effort to bring Martian rocks to Earth by the 2030s, these robotic trailblazers are laying the groundwork for an even bigger leap: human boots on Mars. Their maps of radiation levels, soil composition, and water ice deposits will guide where astronauts land and how they survive. The same drills testing for ancient life could one day extract water for drinking or rocket fuel. In essence, every wheel turn, every laser zap, every soil sample is a stepping stone toward making humanity a multi-planet species. The rover's greatest legacy may be how they've reshaped our cosmic perspective. Mars is no longer just a destination, it's a world with a story, one that mirrors Earth's in unexpected ways. its dried-up river deltas and mineral-rich clays whisper of a time when it might have been as hospitable as our own planet. And if life ever flickered into existence there, even briefly, it would mean the universe is far more generous with biology than we ever dared hope. Until that answer comes, these mechanical explorers will keep scouring the rust-colored landscape, turning science fiction into science fact, one dusty kilometer at a time. In 1963, astronomer Martin Schmidt stared at a perplexing speck of light labeled 3C273 in his spectrograph data. This seemingly ordinary radio source, barely visible through the 200-inch Hale telescope, was about to upend our understanding of cosmic powerhouses. What Schmidt saw defied explanation. Hydrogen emission lines shifted so far into the red that they implied the object was moving away at nearly 15% the speed of light. The implications were staggering. Either the universe's expansion was far more extreme than anyone thought, or this faint dot wasn't a star at all, but something billions of light-years away, and shining with the brilliance of 1,000 galaxies packed into a region smaller than our solar system. Thus began the era of quasars, quasi-stellar radio sources that would challenge every assumption about energy in the cosmos. These cosmic lighthouses, now understood to be supermassive black holes devouring matter at their centers, shine with such ferocity that they outshine their host galaxies. Picture a black hole weighing billions of suns, surrounded by a swirling disk of superheated gas. As material spirals inward, friction heats it to millions of degrees, creating a maelstrom of X-rays, gamma rays, and visible light so intense it can be seen across the observable universe. The most luminous quasars emit energy equivalent to 1 trillion suns, all from a volume no larger than a light day across. Early debates about quasars verged on the surreal. Some scientists proposed they were local objects powered by unknown physics, perhaps even white holes, the hypothetical opposite of black holes spewing matter outward. Others suggested their redshift wasn't cosmological but caused by extreme gravity near neutron stars. The resolution came when astronomers linked quasars to the centers of distant galaxies, their monstrous energy output explained by Einstein's equations governing black hole accretion. The key was realizing these weren't anomalies but extreme examples of processes occurring in every large galaxy, including our Milky Way, where Sagittarius, a star, sits relatively quiet today. Quasars revolutionized astronomy in unexpected ways. Their extreme distances made them cosmic mileposts, helping map the universe's large-scale structure. The absorption lines in their light revealed intervening clouds of primordial hydrogen, offering snapshots of the early universe's chemical composition. Modern surveys have catalogued over 500,000 quasars, some dating back to when the cosmos was less than 1 billion years old, proof that supermassive black holes formed astonishingly early in cosmic history. Perhaps their greatest legacy is what they taught us about galactic evolution. Far from being rare monsters, quasars likely represent a phase most large galaxies undergo, a violent adolescence where feeding black holes blast out enough radiation to sterilize entire systems before settling into quieter adulthood. Their twin jets, often stretching millions of light-years, sculpt their surroundings by heating interstellar gas and suppressing star formation. In this way, quasars aren't just cosmic oddities, they're the universe's architects, shaping the very galaxies that will one day host planets, stars, and perhaps life. Today, the descendants of Schmidt's first quasar continue to illuminate fundamental mysteries. How did black holes grow so massive so quickly? What shuts off their furious accretion? And could our own galactic center ever awaken again? As telescopes probe ever fainter quasars at the edge of time, These blazing beacons remind us that the universe's most violent phenomena often hold the keys to its grandest designs. The Kuiper belt isn't just a ring of icy leftovers, it's a frozen time capsule preserving the solar system's raw ingredients. Stretching from Neptune's orbit out into the void, this vast donut-shaped region holds hundreds of thousands of icy bodies, some as small as pebbles, others rivaling Pluto in size. For decades, it existed only as a theoretical concept proposed by Gerard Kuiper in 1951 as the source of short-period comets. But in 1992, astronomers David Jewett and Jane Liu spotted the first confirmed Kuiper belt object beyond Pluto, a modest icy world designated 1992 QB1. That discovery cracked open a cosmic treasure chest, revealing a dynamic frontier where primordial building blocks never coalesced into planets. What makes the Kuiper belt so extraordinary isn't just its contents, but their pristine condition. Unlike asteroids baked by the sun or comets altered by repeated close passes, these icy relics have lingered in a deep freeze for 4.5 billion years. When NASA's New Horizons spacecraft flew past Pluto in 2015, it didn't just photograph a dwarf planet, it revealed a shockingly active world with nitrogen glaciers and towering water ice mountains. But the mission's piece de resistance came 4 years later when it rendezvoused with Arrokoth, a bi-lobed object resembling a flattened snowman. This tiny world, just 22 miles long, turned out to be a Rosetta Stone for planetary formation. Arrokoth's two lobes, unofficially dubbed Ultima and Thule, show no impact scars or compression fractures, suggesting they gently merged in a slow-motion collision at walking speed. This supported the pebble accretion theory, where planets grow not through violent crashes, but by delicate accumulation of smaller bodies in the early solar system's calm outer reaches. Spectroscopic data revealed organic molecules like methanol ice coating its surface, the same compounds that might have seeded Earth's prebiotic chemistry. Arrokoth wasn't just a curiosity, it was a snapshot of how all planetary building blocks began. Yet the Kuiper belt keeps defying expectations. Some objects, like Haumea, spin so fast they're stretched into oval shapes, while others, like Eris, briefly dethroned Pluto as the solar system's largest dwarf planet. Binary systems where two objects orbit each other are surprisingly common, hinting at a gentler formation process than the asteroid belt's chaotic collisions. Then there's the mystery of ultra-red objects like Sedna, whose crimson hue suggests surface chemistry far more complex than simple ices. Each discovery peels back another layer of the solar system's origin story. The Kuiper belt's greatest secret might still lie in wait. Computer simulations suggest a hypothetical Planet 9 could be lurking in its distant reaches, its gravity shepherding oddball orbits. Whether or not this hidden giant exists, the belt's true value lies in its unaltered relics, frozen blueprints of how our cosmic neighborhood assembled itself. Every icy fragment, every binary pair, every strangely tinted surface is a clue waiting to be decoded, reminding us that the solar system's outer darkness is anything but empty. It's a construction site frozen in time where the planets never finished forming, and where we're just beginning to read the instructions. Imagine if every choice you've ever made, every path taken or ignored, spawned an entirely separate universe where the alternative played out. This isn't science fiction. It's the multiverse hypothesis, a radical theory proposing that our cosmos is just one bubble in an infinite froth of parallel realities. The idea first gained traction in the 1980s when quantum physicists grappled with a peculiar observation. Particles seem to exist in multiple states until measured, as if reality itself hesitates until forced to choose. Some theorists, like Hugh Everett, suggested these aren't just probabilities collapsing, they're all real, each unfolding in its own branching timeline. But the multiverse isn't limited to quantum quirks. Cosmic inflation theory, which explains the universe's rapid expansion after the Big Bang, hints at something even grander. If space-time stretched unevenly like rising dough with random air pockets, each bubble could have cooled into its own universe with unique physics. Picture a cosmic kaleidoscope where one universe has stronger gravity, another has no stars, and yet another might host life forms built from entirely different elements. The most mind-bending version, a mathematical multiverse where every possible structure allowed by equations, no matter how bizarre, exists somewhere in the ultimate everything bagel of reality. Critics argue this sounds less like science and more like metaphysics. Without a way to observe other universes, how can we test the idea? Surprisingly, clues might lurk in our own cosmos. Anomalies in the cosmic microwave background, like cold spots or unusual patterns, could be bruises from collisions with neighboring universes. Others hunt for gravitational echoes from pre-Big Bang events or probe whether fundamental constants, like the strength of gravity, vary subtly across space. Even if definitive proof remains elusive, the multiverse framework has practical value. It helps explain why our universe seems oddly fine-tuned for life. If countless versions exist, it's less surprising that one hit the jackpot. The multiverse's true power lies in how it redefines everything. Suddenly, black holes might be gateways, not endpoints. Dark energy could be leakage from a neighboring reality, and the Big Bang, just one spark in an eternal fireworks show. Whether the theory holds or not, it's already expanded our imagination's horizons, proving that sometimes the most revolutionary ideas aren't about finding answers, but learning to ask bigger questions. The Gaia spacecraft isn't just observing stars, it's rewriting the Milky Way's biography. Since its launch in 2013, this European Space Agency mission has performed the most detailed census of our galaxy ever attempted, measuring the positions, movements, and properties of over 1 billion stars with precision equivalent to spotting a coin on the moon from Earth. But Gaia's true revolution lies in what these measurements reveal when stitched together. A dynamic, three-dimensional map showing not just where stars are, but where they've been and where they're headed over billions of years. Picture our galaxy as a vast, swirling dance floor where each star moves to its own rhythm. Gaia's instruments, 2 telescopes feeding a billion-pixel camera, and spectrometers capture this cosmic ballet in exquisite detail. By observing each star roughly 70 times during its mission, Gaia detects tiny shifts in position that betray their true motions through space. Combined with distance measurements from stellar parallax, observing how stars appear to shift against more distant backgrounds as Earth orbits the Sun, these data points transform flat constellations into a depth-filled starscape. Suddenly, familiar patterns like Orion or Scorpius become temporary arrangements, their shapes distorting over millennia as stars follow their individual paths. What makes Gaia's findings so groundbreaking are the surprises lurking in the data. When scientists compared the orbits of stars with similar chemical compositions, stellar DNA revealing their birthplaces, they uncovered evidence of ancient galactic collisions. The Milky Way wasn't born in isolation. It grew by cannibalizing smaller galaxies, with remnants of these mergers still streaming through our galactic neighborhood like cosmic fingerprints. One such debris field, called Gaia Enceladus, represents a dwarf galaxy that smashed into the Milky Way 10 billion years ago, its stars now scattered throughout our galactic halo. Another discovery, the Sausage Galaxy, left stars moving on radical radial orbits after a more recent impact. Gaia's precision extends beyond archaeology. it's predicting future celestial traffic jams too. The mission has identified stars like Gliese 710, currently 62 light-years away, but on course to pass uncomfortably close to our solar system in just over 1 million years. More dramatically, Gaia's data confirms the inevitable collision between our Milky Way and the Andromeda Galaxy, now pegged to occur in about 4.5 billion years. These aren't just abstract forecasts. They're celestial weather reports made possible by Gaia's ability to measure sideways motions across the sky, a feat previous missions could only dream of. The spacecraft's contributions ripple across astronomy in unexpected ways. By tracking millions of asteroids with unprecedented accuracy, it's refining our understanding of near-Earth object hazards. Its measurements of Starquake's subtle surface pulsations on distant suns are revolutionizing stellar astrophysics, much like seismic waves reveal Earth's interior. Even dark matter studies benefit, as Gaia's maps of stellar motions expose where invisible mass must be lurking to explain observed orbits. Perhaps Gaia's most poetic revelation is how it's redefined our place in the galaxy. For centuries, we assumed the Sun orbited smoothly around the galactic center. Gaia showed we're actually surfing a ripple in the Milky Way's disk, a wave-like distortion caused by interactions with satellite galaxies. This means our solar system isn't just a passenger on this galactic journey. We're riding the crest of a slow-motion tsunami of stars, bobbing up and down through the galactic plane every 64 million years. As Gaia continues its mission, each data release unveils deeper layers of cosmic complexity. Future analyzers may pinpoint stars ejected from other galaxies, trace the Milky Way's missing satellite galaxies, or even identify rogue planets drifting between stars. The mission's ultimate legacy won't be any single discovery, but the way it's transformed astronomy from static snapshots into a living, breathing movie of our galaxy's epic story, one where every star has a role to play and the script is still being written. Enrico Fermi posed his famous question during a casual lunchtime conversation in 1950, but its implications have haunted science ever since. Staring up at a sky teeming with hundreds of billions of galaxies, each home to countless stars and planets, the physicist's blunt inquiry, "Where is everybody?" cuts to the heart of our cosmic solitude. If the universe is so unimaginably vast and ancient, why haven't we encountered even a whisper of other civilizations? This is the Fermi paradox, a riddle that transforms the night sky from a tapestry of wonder into a silent, almost eerie expanse. One compelling answer lies in the sheer rarity of life's ingredients. Even with trillions of planets, the chain from stardust to sentience might be astronomically improbable. Consider Earth's own story. It took nearly 1 billion years for simple cells to emerge after our planet formed, and another 2.5 billion for complex life to evolve. Toss in the need for a stable star, a protective magnetic field, plate tectonics to recycle nutrients, and a moon to stabilize Earth's tilt. What if these aren't just helpful but essential? The rare Earth hypothesis suggests that while microbial life might be common, the leap to multicellular organisms, let alone tool-building intelligence, could be a cosmic lottery few worlds ever win. But what if life isn't rare, just fleeting? Civilizations might flare into existence only to self-destruct, victims of war, environmental collapse, or runaway artificial intelligence. The Great Filter theory posits that some nearly insurmountable challenge lies between primitive life and interstellar expansion. If true, we'd see a universe full of promising planets but no galactic empires, a graveyard of untapped potential. The chilling question then becomes, have we already passed the Great Filter, or is it still ahead of us, lurking in humanity's future? Others argue the problem isn't existence but perception. Advanced civilizations could be all around us, communicating in ways we don't yet recognize. Imagine ants at the base of a radio tower, oblivious to the signals pulsing overhead. SETI searches for radio waves, but what if aliens use neutrino beams, quantum entanglement, or something beyond our physics? Or perhaps they're deliberately avoiding us, adhering to a galactic prime directive to let young species like ours develop undisturbed. The zoo hypothesis suggests we might be quarantined in a cosmic wildlife preserve, observed but not contacted. Then there's the unsettling possibility that we're simply too early. The universe is 13.8 billion years old, but it's still in its infancy compared to the trillions of years ahead. Most stars, red dwarfs, will shine for hundreds of times longer than the current age of the cosmos. If intelligence tends to emerge later in the universe's lifespan, we might be cosmic pioneers, alone only because no one else has caught up yet. The Fermi paradox isn't just about aliens, it holds up a mirror to humanity. Each proposed solution forces us to confront our assumptions about life, technology, and survival. Are we special, doomed, or just impatient? As our telescopes grow sharper and our probes venture farther, the silence grows louder, reminding us that the universe owes us no answers. But the search itself for signals, biosignatures, even alien artifacts transforms the question from a thought experiment into a mission. After all, if we're truly alone, that's one kind of miracle. And if we're not, the discovery would rewrite not just science, but our very place in the story of existence. On a quiet August night in 1977, a radio telescope in Delaware, Ohio, picked up something extraordinary, a burst of noise so powerful, so unusual, that astronomer Jerry Amon circled it on the printout in red pen and scribbled, "Wow." Next to it, that single annotation gave the signal its name, but the mystery behind those 72 seconds of static would echo through decades of scientific debate. The numbers 6EQUJ5, encoded in the printout, represented a narrowband radio emission at 1420 MHz, a frequency where cosmic noise is minimal and where hydrogen, the universe's most abundant element, naturally resonates. It was as if the cosmos had shouted directly into our receivers, then fell silent. What made the wow signal so electrifying wasn't just its strength, 30 times louder than background noise, but its characteristics. Unlike natural sources like pulsars or quasars, which scatter energy across multiple frequencies, this signal was clean and focused, precisely the fingerprint scientists predicted an artificial transmission would have. Even more intriguing was its motion. The signal peaked and faded over 37 seconds, matching Earth's rotation, exactly what you'd expect if it originated from deep space. The Big Ear telescope's twin-feed horns detected it in one beam but not the other, suggesting a localized source. Yet despite exhaustive follow-ups, including scans by the SETI Institute's Allen Telescope Array, the signal never repeated. Theories about its origin range from the mundane to the extraordinary. Could it have been a rogue satellite or military transmission? Unlikely, no known human technology matched its frequency or drift rate. A passing comet. Later research showed none were in the right patch of sky chance alignment with a pair of comets in 2017, proved equally unconvincing. The most tantalizing possibility, an intentional beacon from an extraterrestrial civilization, remains unproven but unforgettable. The WOW signal emerged from the constellation Sagittarius, near the galactic center, where billions of stars cluster in a region ripe for life. Decades later, the signal's legacy endures not as proof of aliens, but as a lesson in scientific humility. It reminds us that the universe is vast enough to hide profound mysteries in plain sight, and that sometimes the most meaningful discoveries are the ones we can't explain. Every time a new telescope scans that same patch of sky, it carries a quiet hope not just to solve the puzzle, but to prove that in the cosmic silence, we might not be the only ones listening. The pioneer plaques weren't just metal engravings, they were bottles tossed into the cosmic ocean, carrying whispers of humanity across the interstellar void. When Pioneer 10 and 11 launched in 1972 and 73, they carried more than scientific instruments. Bolted to their antenna supports were 12 by 9-inch gold anodized aluminum plates, etched with symbols meant to introduce Earth to any civilization that might one day intercept them. Designed by Carl Sagan and Frank Drake, with artwork by Sagan's then-wife Linda Saltzman, these humble discs became humanity's first physical messages to the stars, a blend of science, art, and sheer optimism encoded in geometric precision. At first glance, the plaque symbols seem cryptic, a mix of lines, diagrams, and silhouettes, but every mark was meticulously chosen to convey universal truths. The most prominent feature, a nude male and female figure, arms raised in greeting, standing before the silhouette of the Pioneer spacecraft for scale. While the depiction sparked debates about modesty and representation, its purpose was clear: to showcase human biology without cultural bias. To their left, a radial starburst pattern pinpoints Earth's location relative to 14 pulsars, cosmic lighthouses, whose unique frequencies serve as galactic GPS coordinates. Each pulsar's spin rate is denoted in binary, acting as a countdown timer any advanced civilization could decode to trace our solar system's origin point. Even the hydrogen atom's hyperfine transition, a fundamental constant of nature, was included as a universal unit of measurement and time. What's often overlooked is how radical this idea was. Before the Pioneer plaques, humanity's attempts to reach extraterrestrials had been fleeting radio waves, ephemeral signals that vanished into the ether. These plaques were different. They were tangible, durable, and utterly irreversible. Unlike a radio transmission that fades, these artifacts could drift for millions of years, surviving long after human civilization might vanish. They carried no threats, no politics, just a quiet declaration: we are here, and we wondered if you are too. Yet the plaques also reveal the limits of human perspective. Symbols we consider universal, like an arrow indicating the spacecraft's trajectory, might be meaningless to a species without projectile technology. The pulsar map assumes extraterrestrials perceive space as three-dimensional and share our mathematical frameworks. Even the human figure's upright posture presumes bipedalism is a cosmic norm. These unconscious biases highlight the challenge of communicating across unimaginable cultural and biological divides. The legacy of the Pioneer plaques extends far beyond their physical journey. They inspired more ambitious projects like the Voyager Golden Records, which carried sounds and images of Earth. They sparked philosophical debates about humanity's right to announce its presence. Could such messages attract hostile attention, or are we ethically obligated to reach out? And they reframed space exploration as not just a scientific endeavor, but a cultural one, where every probe carries fragments of the civilization that built it. Today, Pioneer 11 sails silently through interstellar space, its plaque untouched and unread. Pioneer 10, now defunct, drifts toward the constellation Taurus, though its signal faded in 2003. Their messages may never be found, but that's beside the point. Like a message sealed in a bottle and cast into the sea, their value lies in the act itself. They are declarations of curiosity, crafted with the hope that somewhere, someday, another intelligence might pause and ponder the hands that made them. In a universe that often feels indifferent, the Pioneer plaques remind us that the desire to connect, to say you are not alone, is perhaps the most human impulse of all. Frank Drake didn't just want to guess about aliens, he wanted to calculate the odds. In 1961, the young astronomer scribbled a deceptively simple equation on a chalkboard at the first SETI conference, distilling the vast unknowns of cosmic biology into 7 manageable variables. This wasn't just math, it was a roadmap for quantifying humanity's cosmic loneliness. The Drake equation breaks down like this: multiply the rate of star formation by the fraction of stars with planets per star that could support life, the odds life actually emerges, the chance it becomes intelligent, the fraction that develops technology to communicate, and finally, how long those civilizations last before vanishing. Crunch those numbers and you get n, the number of detectable civilizations in our galaxy right now. What's brilliant about the equation isn't its precision, it's how it exposes our ignorance. Take the third term, planets in the Goldilocks zone. When Drake first wrote his equation, we knew of 0 exoplanets. Today, telescopes like Kepler and TESS have confirmed over 5,000, suggesting nearly every star hosts worlds. But then comes the next hurdle. Does life always arise given the right conditions? On Earth, it appeared shockingly early, within a few 100 million years of the planet cooling. Does that imply life is inevitable, or was Earth just lucky? The equation doesn't answer this, it highlights where to focus research, turning philosophy into testable science. The real friction comes with the final terms. Even if intelligence and technology evolve, how long do civilizations survive? A century, a million years? This variable, L, is the equation's dark shadow. Imagine 2 scenarios. If the average civilization lasts only a few centuries before self-destructing through war, climate collapse, or AI mishaps, then the galaxy might be littered with silent ruins. But if even a handful endure for tens of thousands of years, the cosmos could hum with conversation. Drake's own estimates swung wildly, from 10 to 10,000 communicative societies in the Milky Way. Critics dismiss the equation as guesswork dressed in math, but that misses the point. Like Copernicus shifting Earth from the cosmic center, Drake's formula forces us to confront assumptions. Why wouldn't life be common? Why wouldn't intelligence emerge? Each discovery, from extremophiles thriving in acid to methane seas on Titan, pushes the plausibility needle. The equation's power lies in its adaptability. As we learn more about ocean worlds or decode the origins of life in labs, we refine the variables, inching closer to an answer. Perhaps the equation's greatest legacy is how it bridges science and wonder. It's a reminder that the search for aliens isn't just about antennas and algorithms. It's about understanding our own fragility in a universe that may be brimming with voices, all asking the same silent question: is anyone out there? And until we know for sure, Drake's scribbled formula remains the closest thing we have to a cosmic phone book, its pages half empty, waiting to be filled. The universe doesn't just have constants it hangs on them. Tweak the strength of gravity by a fraction, or nudge the charge of an electron, and stars wouldn't ignite, atoms would fly apart, and life as we know it would be impossible. This eerie precision isn't coincidence, it's the heart of the anthropic principle, the observation that the cosmos seems inexplicably tailored for our existence. At first glance, it sounds almost mystical. Are we here because the universe permits it, or does the universe permit it because we're here? One way to frame this is through the cosmic lottery analogy. Imagine a universe-generating machine with endless dials, each controlling a fundamental force or constant. Spin those dials randomly, and nearly every combination creates a dead, chaotic void. But somehow, against inconceivable odds, our universe landed on the perfect settings for galaxies, planets, and conscious beings to emerge. Physicists call this the fine-tuning problem. and the numbers are staggering. If the strong nuclear force were 2% weaker, protons wouldn't bind, leaving no atoms beyond hydrogen. If dark energy's density were slightly higher, the universe would have expanded too rapidly for stars to form. The list goes on, each parameter balanced on a razor's edge. This precision has sparked debates that blur the lines between science and philosophy. Some lean into the multiverse explanation. If infinite universes exist with random laws, statistically, a few must hit the jackpot for life, and we're simply in one of the lucky ones. Others see intentionality, a universe engineered with purpose, though by what or whom remains unanswered. Even agnostic scientists admit the puzzle demands some explanation, whether it's undiscovered physics, a deeper layer of reality, or something beyond current comprehension. The anthropic principle also reframes our place in the cosmos. Instead of being accidental inhabitants of an indifferent universe, we're active participants in a reality that allows us to observe it. Think of it like a cosmic version of the observer effect in quantum mechanics. Our very existence as conscious observers may be entwined with the universe's fundamental structure. This doesn't prove design, but it does challenge the assumption that life is a fluke. Critics argue the principle is a tautology. Of course, we find ourselves in a universe compatible with life because we couldn't exist otherwise. But that misses the deeper question: why does such a universe exist at all? Whether the answer lies in undiscovered dimensions, a grand simulation, or pure chance, the anthropic principle forces us to confront the unnerving elegance of reality. It's not just about why we're here, it's about why here allows us to be. Ultimately, this principle doesn't solve the mystery, it deepens it. Every time we measure a fundamental constant with greater precision, or discover another improbable balance in nature, we're reminded that our universe is either unimaginably lucky, or we're missing a fundamental piece of the puzzle. And that tension between chance and design, observation and existence, is what makes the anthropic principle one of the most profound, humbling ideas in all of science. It's not a conclusion, but an invitation to keep questioning everything we think we know. Alan Guth was sitting at his desk at Stanford in 1979 when a radical idea struck him. What if the universe didn't just expand after the Big Bang, but underwent a runaway growth spurt that stretched space itself faster than light? That midnight insight became cosmic inflation theory, a solution to some of cosmology's most stubborn puzzles. Picture this: in the first trillionth of a trillionth of a trillionth of a second after creation, the universe didn't just grow, it exploded from smaller than an atom to the size of a grapefruit, doubling in scale at least 60 times in a cosmic blink. This hyper-expansion wasn't powered by conventional physics, but by a bizarre state of vacuum energy that briefly turned gravity into a repulsive force, flinging space-time apart like dough in an oven set to warp speed. What makes inflation so revolutionary isn't just the scale of expansion, it's how neatly it solves three cosmic mysteries in one swoop. First, the horizon problem. Why does the universe look so uniform in all directions? Distant regions of space shouldn't have had time to reach the same temperature, yet the cosmic microwave background is smooth to 1 part in 100,000. Inflation's answer: those regions were once cheek by jowl before being violently stretched apart. Second, the flatness problem. Why is the universe's geometry so perfectly balanced between collapsing and expanding? Inflation's hyper-stretching would have ironed out any curvature, like blowing up a balloon to cosmic proportions. Finally, the magnetic monopole problem. Where are the heavy, exotic particles predicted by grand unified theories? Inflation diluted them to near non-existence, sweeping them to the far edges of reality. Yet for all its elegance, inflation remains tantalizingly just out of reach. The theory predicts ripples in spacetime called primordial gravitational waves, imprinted during inflation's crescendo. These would leave a distinct swirling pattern in the cosmic microwave background's polarization, a smoking gun cosmologists have hunted for decades. When the BICEP 2 team announced they detected this signal in 2014, the excitement was electric until interstellar dust was found to mimic the same pattern. Current experiments like the Simons Observatory and future space missions aim to filter out this cosmic static, but for now, inflation's definitive proof remains elusive. The theory's implications stretch beyond cosmology. If inflation happened once, could it happen elsewhere, spawning bubble universes with different physical laws? Some models suggest our observable universe might be one such bubble in an eternally inflating multiverse, a fractal foam of realities where constants like gravity or the speed of light are reshuffled in each pocket. It's a dizzying thought. What we call the universe might just be our local neighborhood in a far vaster, stranger metaverse. Critics argue inflation is too flexible, able to explain almost any observation by tweaking parameters. Without direct evidence, does it cross from science into philosophy? Guth himself admits the theory's details are still being refined, with competing models like chaotic inflation or eternal inflation offering variations on the theme. But the core idea, that spacetime underwent a violent, exponential stretch, has become cosmology's leading origin story, weaving the Big Bang into a grander cosmic narrative. Perhaps inflation's greatest gift is how it reshaped our sense of cosmic time. Those first instants weren't just a prelude, they were the crucible where the universe's fate was forged. Every galaxy, every star, every atom owes its existence to that fleeting moment when gravity flipped its script and space itself got a head start on everything we know. And somewhere out there, in the faintest whispers of ancient light, the echoes of that primeval expansion might still be waiting to be heard. In 1998, two teams of astronomers made a discovery so shocking it turned cosmology upside down. They weren't looking for dark energy, they were measuring distant supernova to calculate how much the universe's expansion should be slowing down due to gravity. Instead, their data revealed the opposite. The cosmos wasn't just growing, it was accelerating, as if some invisible force was pushing galaxies apart faster and faster over time. The implications were staggering. Either Einstein's theory of gravity was wrong on cosmic scales, or a mysterious energy permeated space, counteracting gravity's pull. The latter explanation won out, and dark energy, an enigmatic repulsive force, became the dominant theme in modern physics. What makes dark energy so baffling isn't just its existence, but its sheer dominance. Accounting for roughly 68% of the universe's total energy budget, it outweighs both dark matter and ordinary matter combined. Think of it like this: if the cosmos were a pie, the atoms making up stars, planets, and our bodies would be a mere 5% of a single slice. Dark matter would claim another 27%. The rest, pure dark energy, an unseen driver stretching the very fabric of reality. The simplest explanation ties it to Einstein's cosmological constant, a sort of energy cost of empty space itself. But here's the catch: quantum field theory predicts this vacuum energy should be 120 orders of magnitude stronger than observed. That's not just a rounding error, it's the worst mismatch in science. Alternative theories abound. Maybe dark energy isn't constant but evolves over time, a concept called quintessence, where a dynamic field permeates space with changing strength. Others propose modifications to Einstein's gravity, suggesting our understanding of spacetime breaks down at cosmic distances. Then there's the radical idea that dark energy hints at extra dimensions, with gravity leaking into unseen realms. The problem: no direct evidence supports any single explanation. Dark energy's fingerprints are indirect, written in the way supernova fade, in the large-scale distribution of galaxies, and in subtle patterns in the cosmic microwave background. The stakes couldn't be higher. Dark energy determines the universe's ultimate fate. If it strengthens, it could trigger a big rip, shredding galaxies, stars, and even atoms apart in a catastrophic end. If it weakens, gravity might regain control, collapsing the cosmos in a big crunch. Or perhaps it'll balance perfectly, allowing expansion to continue quietly into eternity. Upcoming telescopes like the Vera Rubin Observatory and ESA's Euclid mission aim to map dark energy's influence with unprecedented precision, searching for clues in the shapes and motions of billions of galaxies. Yet the deepest lesson of dark energy may be humility. Just when we thought we understood the cosmos, it revealed a force so pervasive it controls reality's fate, and so elusive we can't even say what it is. It's a reminder that the universe still holds mysteries too profound for our current frameworks, waiting for the next Einstein to shine a light into the dark. The future of astronomy isn't just about bigger telescopes, it's about rewriting the rules of cosmic exploration. Imagine a telescope so powerful it could map the surface of an exoplanet, or a probe venturing beyond our solar system to sniff the atmospheres of alien worlds. This isn't science fiction, it's the roadmap for the next century. Take the Nancy Grace Roman Space Telescope, set to launch in 2027. With a field of view 100 times wider than Hubble's, it won't just study individual galaxies, it'll conduct a cosmic census, uncovering millions of exoplanets through gravitational microlensing while peeling back the mysteries of dark energy. Then there's the extremely large telescope in Chile, with a 39-meter mirror so precise it could spot a car headlight on the moon. This behemoth might finally capture the first direct image of an Earth-like planet orbiting another star, analyzing its atmosphere for biosignatures like oxygen or methane. But the real game-changer lies beyond light. The Laser Interferometer Space Antenna, or LISA, will launch in the 2030s as the first gravitational wave observatory in space. While ground-based detectors like LIGO catch the collisions of stellar mass black holes, LISA trio of spacecraft spaced 2.5 million kilometers apart will sense low-frequency ripples from supermassive black holes merging at the dawn of time. It's like adding sound to a silent movie. Suddenly, we'll hear the universe's hidden symphonies, from the death spirals of primordial black holes to the tremors of spacetime itself. Meanwhile, interstellar ambitions are heating up. Breakthrough Starshot aims to send gram-scale probes to Alpha Centauri at 20% light speed, propelled by ground-based lasers. These nanocraft, equipped with cameras and sensors, could beam back images of Proxima b within our lifetimes. Closer to home, missions like Europa Clipper and Dragonfly will hunt for life in our solar system's hidden oceans, Europa's icy depths, and Titan's methane lakes. Even Pluto might get a second visitor, with proposals for orbiters that could study its glaciers and nitrogen geysers in detail. Yet the most profound discoveries may come from tools we haven't even imagined. Quantum sensors could detect dark matter particles streaming through Earth. Neutrino observatories might trace the fiery hearts of distant galaxies, and artificial intelligence, trained on petabytes of telescope data, could spot anomalies no human would ever notice, perhaps even signals from extraterrestrial civilizations. The questions driving these missions are as old as humanity itself. Are we alone? How did the universe begin? What's beyond the cosmic horizon? For millennia, we've gazed up with wonder. Now, we're on the verge of turning that wonder into knowledge. The next era of astronomy won't just fill textbooks, it could redefine our place in the cosmos, revealing realities stranger than anything we've dared to dream. These 38 milestones aren't just points on a timeline, they're stepping stones across a river of wonder, each one revealing how much we've learned and how much we've yet to understand. Think about it. We went from believing the stars were fixed to a celestial sphere to mapping the ripples of space-time from colliding black holes. We once saw Earth as the universe's center. Now we debate whether we're one bubble in an infinite cosmic foam. And yet, for every mystery solved, like the true nature of quasars or the origin of cosmic microwave background, a dozen new questions emerge. Dark energy's relentless push, the enigma of dark matter, the search for life beyond Earth, these aren't just puzzles. They're invitations to keep exploring. What's extraordinary isn't just the scale of our progress, but the humility it demands. Every time we build a better telescope or launch a more ambitious probe, the universe responds by showing us how much we've underestimated its complexity. Take the James Webb Space Telescope, designed to answer questions about the earliest galaxies. It instead presented us with cosmic toddlers too massive and too mature for our models to explain. Or consider gravitational wave astronomy, a field that didn't even exist a decade ago, now rewriting our understanding of black hole mergers. The story of astronomy isn't one of closing chapters, but of turning pages to find the next plot twist. And the tools we're building for tomorrow promise revelations we can barely fathom. The Vera Rubin Observatory will scan the entire southern sky every few nights, catching asteroids, supernova, and who knows what else in its relentless gaze. The square-kilometer array, with its thousands of radio antennas, will listen for the faintest whispers from the cosmos's dawn. Missions like Europa Clipper and Dragonfly will probe alien oceans and methane lakes, asking the oldest question of all: are we alone? The arc of discovery keeps bending toward bigger, bolder questions because that's what the universe rewards, not just answers but better ways to wonder. So what's next? Maybe we'll finally detect dark matter particles in an underground lab. Perhaps a radio telescope will pick up a signal that's unmistakably artificial. Or some sharp-eyed grad student will spot an anomaly in old data that cracks open a new branch of physics. The only certainty is this: the cosmos has never let curiosity rest. Every discovery is both an ending and a beginning, a solution to one riddle and the first clue to the next. That's why astronomy isn't just a science, it's the ultimate adventure. It's for everyone who's ever looked up and felt that itch to know more. Whether your favorite milestone is Galileo turning his telescope to Jupiter or the haunting silence of the Wow signal, each one reminds us that the universe is stranger, more beautiful, and far more generous with its secrets than we ever dared hope. The night sky isn't just a sight, it's a conversation, and it's far from over. So grab your telescope, your curiosity, or just a comfy blanket, and keep looking up. The next great discovery might have your name on it. Some of astronomy's greatest discoveries don't come from towering observatories or billion-dollar space telescopes. They start with ordinary people staring at their laptops in living rooms and coffee shops. Take the case of Hannes Voorwerp, a strange green cosmic cloud that baffled professionals until Dutch schoolteacher Hanny van Arkel spotted it while classifying galaxies on Galaxy Zoo. Her sharp eyes and curiosity unlocked a new class of astronomical objects, proving that groundbreaking science doesn't always wear a lab coat. Platforms like Zooniverse have turned the internet into a global research lab, where anyone with a Wi-Fi connection can hunt for supernova, track Martian weather, or sift through data from NASA, a test mission to flag potential exoplanets. It's not just busy work. These volunteers have co-authored scientific papers and even named asteroids. When NASA Kepler telescope unleashed a flood of light curves from distant stars, it was citizen scientists who helped identify star spot patterns and planetary transits that algorithms missed. In 2017, a retired electrical engineer named Andrew Gray discovered a four-planet system simply by scrolling through data on his tablet, proof that cosmic breakthroughs don't discriminate between PhDs and passionate amateurs. The tools are surprisingly accessible. Projects like Backyard Worlds, Planet 9 invite users to scan infrared maps for moving dots that might be rogue planets or brown dwarfs lurking near our solar system. Others, like Asteroid Hunters, train volunteers to identify space rocks that could threaten Earth. The thrill isn't just in the hunt, it's in the real-world impact. When Australian amateur Terry Lovejoy discovered a comet in 2011, his findings helped researchers study the composition of interstellar ice. And let's not forget the ALPO Association of Lunar and Planetary Observers, where Backyard Telescope users document Jupiter's storms or Mercury's phases, contributing decades-long datasets that professionals rely on. What makes this collaboration so powerful is how it mirrors astronomy's earliest days, when farmers and philosophers alike charted the stars with nothing but naked eyes and notebooks. Today's citizen scientists might use apps instead of astrolabes, but the spirit remains the same: curiosity fueled by the sheer joy of discovery. Whether it's a teenager in Mumbai spotting a variable star's flicker or a retiree in Toronto tracing dust storms on Mars, these volunteers remind us that the universe doesn't belong to any one group. It's a shared frontier, waiting for anyone willing to look up and wonder. The next great astronomical revelation might not come from a mountaintop observatory, but from someone scrolling through telescope images on their lunch break. And that's the real magic, not just the discoveries themselves, but the proof that science is, and always has been, a conversation where everyone gets to speak. Caroline Herschel spent her early life scrubbing floors and singing for her supper in Hanover, Germany, until her brother William changed everything by bringing her to England to assist in his astronomical pursuits. What began as housekeeping duties soon transformed into something extraordinary. By 1786, Caroline was discovering comets on her own, meticulously sweeping the night sky with homemade telescopes. Her 8 comet discoveries shattered the assumption that astronomy was solely a man's domain, and her catalogue of nebulae laid groundwork for future deep sky studies. Yet when King George III awarded her a salary for her work, making her the first woman officially recognized for scientific contributions, it was half what her male counterparts earned. Her legacy wasn't just in the stars she mapped, but in the cracks she made in the glass ceiling above her. Jump forward a century, and Henrietta Swan Leavitt was working as a computer at Harvard College Observatory, earning 25 cents an hour to analyze photographic plates of stars. While her male colleagues focused on grand theories, Leavitt noticed something others overlooked: a pattern in the pulsations of Cepheid variable stars. Her discovery that their brightness correlated perfectly with their pulsation period became the cosmic yardstick Edwin Hubble later used to measure galactic distances. This revelation rewrote the scale of the universe, yet Leavitt's name was conspicuously absent from Nobel nominations. Her work, though foundational, was buried in the footnotes of history until now. Then there's Vera Rubin, who in the 1970s stared at the rotation curves of galaxies and saw gravity's stubborn mismatch. The stars at the edges of spiral galaxies moved too fast to be held by visible matter alone. Her meticulous observations became the strongest evidence for dark matter, yet the Nobel Prize Committee overlooked her repeatedly. Male colleagues who expanded on her work received accolades, while Rubin faced skepticism thinly veiled as condescension. "Fame is fleeting," she once remarked. "My numbers mean more to me than my name." The story crescendos with Jocelyn Bell Burnell, a graduate student in 1967 who spotted rhythmic pulses in radio telescope data. signals so precise they were initially dubbed LGM for Little Green Men. These turned out to be the first pulsars, the spinning corpses of massive stars. But when the Nobel Prize was awarded for the discovery, Bell Burnell's supervisor and his colleague took the credit. Decades later, she reflected with grace, demarcation disputes between supervisor and student are always difficult. Her discovery revolutionized our understanding of stellar death, even if the recognition didn't follow. These women didn't just contribute to astronomy, they redefined what was possible in the face of systemic barriers. Cecilia Payne-Gaposchkin's Harvard thesis proved stars were made mostly of hydrogen, yet her male advisor dismissed it as impossible before later taking credit. Margaret Burbidge fought to use telescopes at Mount Wilson Observatory, then restricted to men, by posing as her husband's assistant. Their struggles weren't just personal, they were part of a pattern that silenced half the human race's potential to explore the cosmos. The lesson here isn't just about correcting historical oversights. It's about recognizing how much richer astronomy becomes when diverse minds engage with its mysteries. When women like Nancy Grace Roman, the mother of Hubble, champion space telescopes, or when Andrea Ghez uses adaptive optics to reveal the supermassive black hole at our galaxy's core, they're not just adding to science. They're proving that the universe reveals its secrets best when all of humanity is invited to look up and ask questions. The stars don't discriminate.